PL 992 3044, PLTR 92 3044, force-free time-harmonic plasmoids. Jack Nachamkin, University of Dayton Research Institute, Dayton, Ohio 45469, October 1992, Interim Report. 2V131, Phillips Laboratory Propulsion Directorate Air Force, Material Command Edwards Air Force Base CA 93524 to 7001. Notice: when U.S. government drawings, specifications, or other data are used for any purpose other than a definitely related government procurement operation, the fact that the government may have formulated, furnished, or in any way supplied the said drawings, specifications, or other data is not to be regarded by implication or otherwise, or in any way licensing the holder or any other person or corporation, or conveying any rights or permission to manufacture, use or sell any patented invention that may be related thereto. Forward. This report was prepared by University of Dayton Research Institute, Dayton O, under Contract F 0461188C 020, for operating location AC, Phillips Laboratory, Edwards AFB, CA 93524 7001. Project manager for Phillips Laboratory was Frank Mead. This report has been reviewed and is approved for release and distribution in accordance with the distribution statement on the cover and on the SF Form 298. Frank B. Mead, Project Manager. Stephen L. Rogers, Chief, Emerging Technologies Branch. Leonard C. Brolin, L., Colonel USAF, Director. Fundamental Technologies Division. Rani Adams, Public Affairs Director. DTTDA. Excision FO NTI's Chrysiotic Tag Unconst Justification by Duba, A1 Avanti. Report documentation page form approved OM No 0204 to 0188 October 1992 1. Agency use only leave bank 2. Report date tile and subble force-free time-harmonic plasmids, authors Jack Nachamkin 7. Performing organization NAMIS, and addresses University of Dayton Research Institute, Dayton, Ohio 45469%, sponsoring, monitoring agency names, and addresses Phillips Laboratory Olak Pella, RKF Edwards, AFB, 93524 to 768011. Supplementary notes COSATI codes, 23rd, 29th, 12. Distribution. Availability Statement 3. Report type and gates covered Tattery November 91, July 92 5. Funding numbers approved for public release. Distribution is unlimited C. F04600 and 1188C 0020 PE, 62302 PR, 3058 TA. 0006 Performing Organization Report, Number 19. Sponsoring, Monitoring Agency Report Number, PLTR, 92, 3044, 126, Distribution, Cool, 13. Abstract. Man, 350 word, a heretofore unexplored solution of Maxwell's equations is investigated for time-harmonic waves in a partially phonized gas. The analysis is focused on the spherically symmetric cases that behave like electromagnetic energy trapped in the form of a plasmoid. It will be shown that a critical frequency exists, below which the current cannot be carried by electrons and the plasmoid remains stable. Resonant sizes will be shown to extat such that plasmoid will not exchange energy with their external surroundings, and their boundary conditions can be met by vacuum solutions to Maxwell's equations. Virial analysis calculates free charge density and critical frequency to be consistent with Newtonian mechanics and classical electromagnetics. A stable vortical motion of the plasma will be shown to exactly cancel the dominant component of the electromechanical stresses, with the residual stresses being a strongly decreasing function of frequency. 14. Sunect Teams Drift. Electromagnetic Theory, Electromagnetics, Force-Free, Maxwell's Equations, Plasmoids, Plasma, Radiation, Stability, Virial Theorem, Vortex, Vorticity 15. Number of pages, Passcode 12. Howley Classification 18. Secondary Classification Security Classification. 20. Tation of Abstract of Report. Unclassified min 5 January 30th, 2040. 5,500 of this page. Unclassified of abstract unclassified. 111 Sadi Reels. Standard form. 258. Reverend 2, 45. Contents. Section Preface. Summary L. Introduction. Second, Mathematical Preliminaries. Third, Time-Harmonic Force-Free Electromagnetic Fields. Fourth, Radiation and Ideal Plasmoids. Pag 10 Fifth, Electronic Currents. 12 Sixth, Virial Considerations. Vil Electromagnetic Stresses. 14 18 Vortical Plasma Stabilization. 23 9th Discussion. 31 Appendix. Of 38 Appendix B Appendix. C Appendix D Appendix. E Appendix F Appendix G References. 50 53 54 55. 111. Figures. 1. Uniform current in a cylindrical wire. 2. Ergodic flow lines R equal to 4.493. Ergodic blow lines R equal to 3.374. Ergodic bow lines R equal to 2.85. Perturbation of the J field 6. Plasmate SS. Cavity field 7. The neutral plasma 8. Forces on a moving electron 9. Effects of local charge perturbations 10. Drift due to field curvature 11. The stress tensor 12. Matching boundary conditions 13. Matching boundary conditions in a resonant cavity are 1. The plasmoid far field 12 12 13 17 19 25 34. Preface. Work in this paper is primarily aimed at the elementary development of the theory of time-harmonic electromagnetic fields that have the force-free form for Plush electric and magnetic fields, as well as the current. It is hoped that enough detail is included for the paper to be used as a tutorial for the majority of people who have never encountered force-free fields and wish to investigate what, at first blush, seems like an impossible solution of Maxwell's equations. The research was spurred by attempts to understand experimental results obtained in the late 1960s and early 1970s in areas of fusion weapons and laser fusion in Los Alamos. At the time, there were anomalies such as unexplained symmetries in the fragments of disintegrating laser-irradiated pellets and puzzles about compression and stability of small spherical volumes of plasma in the presence of high-intensity electromagnetic fields. During that time, and since, a large number of people investigated many of the phenomena of interest without fully being able to resolve all the CLS or plasma inertial confinement. No claims will be made that this work will make any of the inertial confinement problems easier. In the period of close to 2 decades after performing the original work, some of the insights gained into solutions of Maxwell's equations in a conducting fluid were seen to have relevance beyond the controlled fusion community. In particular, finite, sized, non-plane wave, force-free time-harmonic electromagnetic excitations, with electric and magnetic field vectors parallel to each other everywhere, in the presence of plasma current, seem to be undiscovered solutions that deserved exploration. What makes such solutions interesting is that the Poynting vector is identically zero everywhere inside a finite-sized force-free field, and it cannot dissipate unless either its boundary is radiating or internal stress make it break up. Classically, these fields cannot exist in a vacuum. In a quiescent plasma, internal stresses on their accompanying currents can disrupt them as soon as they are created. By a remarkable coincidence, the electromechanical stresses manifest themselves mainly as a pressure field, which can be nearly exactly balanced by vortical fluid model. This vortical fluid field, otherwise called Beltrami motion, is also self-disruptive, by itself, in a compressible fluid. The alleged simultaneous occurrence of the force-free time-harmonic electromagnetic field and the matching vortical fluid motion with a well-defined boundary will be called a plasmoid. Although the solutions to Maxwell's equations, coupled to fluid dynamic modes, do not seem to violate any physical principles, it is not immediately obvious how one would go about producing them. Mathematically, it, at first, seemed possible that such excitations could exist at all frequencies. A more physical approach showed that below a critical frequency, determined by its size, a plasmoid represents a plasma state. At V, a local energy maximum, that is, it is unstable. In addition, electrons are unable to carry the current below this critical frequency. Above the critical frequency, the physics becomes more interesting, as the current is carried by the electrons and the plasma is at an energy minimum, even though the total energy is positive. The author believes that a number of observed phenomena, including ball lightning, are fireballs and charge clusters that occur in strong plasma discharges, may be described, at least in part, by the plasmoids in this theory. Some of the nonlinear effects of powerful lasers impinging on small spheres of material might also produce plasmoids of the type to be described. The work in this paper being only a start, the theory is incomplete. A great deal of work still remains to be done to determine whether real plasmas at elevated temperatures can sustain force-free plasmoids. Open questions are quantum and quantum electrodynamic effects, and interactions with the electromagnetic zero-point background remain to be investigated. Puzzles concerning external fields, surface currents and plasmoid interactions also need solving, and may involve quantum effects. The possibility that unexplored and, as yet, unknown principles are involved in explaining the existence of compact, stable, autonomous, highly energetic concentrations of plasma and/or electromagnetic fields cannot be overlooked. Much of this work can be conducted with quiet thought in libraries and in front of a computer. In general, however, a complementary experimental program is absolutely necessary at this point to focus the theoretical effort. The author would like to thank Dr. Franklin B. Mead, Chief of the Future Technologies section in the Astronautical Sciences Division at the Air Force's Phillips Laboratory, for the interest he has shown in this work. Without Dr. Mead's encouragement and kind hospitality, the ideas in this work may never have been developed even this far. Research in such areas is very risky, and I acknowledge Dr. Mead's bravery, in an era of rapidly diminishing funds, for the support of the work. Thanks are also due to the University of Dayton Research Institute and Dr. Eugene Gerber for providing a pleasant atmosphere for conducting research. VI. Force-free Time-Harmonic Plasmoids. Summary. Maxwell's equations allow time-harmonic solutions wherein the electric and magnetic fields are parallel to each other and both have the force-free form. These fields are accompanied by a time-harmonic current field that also has the force-free form. Such solutions are postulated as a model for Lug-lived spherical plasmoids. It is shown that a critical frequency exits, which depends on the size of the plasmoid. Below this frequency, the time-harmonic current cannot be carried by electrons in a plasma. Above the critical frequency, local perturbations of the current tend to increase the total energy, lending stabilization. The electromechanical stresses induced by the fields on the current-carrying electrons can be balanced to a high degree of accuracy by vortical motion of the supporting plasma. The velocity field of the vortex also has the force-free, Beltrami form. This vortical fluid motion is stable and exactly compatible with the stresses in the plasmoid. Although it is a theoretical possibility for currents to flow on the outside of a plasmoid to isolate it from external fields, free space time-harmonic fields can be found that have both their electric and magnetic fields parallel to each other over the surface of a spherical plasmoid having a resonant size, making the fields continuous at the boundary. Surface currents can thereby be eliminated. Only at a resonant size can the outward-going radiation due to the fields at the surface of the plasmoid be milled, and the external fields be joined continuously to the internal fields. An example is given showing that a 1 megajoule force-free plasmoid in an STP atmosphere could be described with physically reasonable parameters. L. Introduction. Bostic described a plasmoid as a structure made of plasma, whose form is determined by the magnetic field it carries, along with its cell. 1. His definition attempted to describe the coherent discharges he encountered emanating from a plasma gun. These plasma structures are evidently very stable, have long lifetimes, and can interact with each other. 2. Since the time of Bostic's original work, plasmoid-like structures have been reported by other investigatora. 3. Under different conditions they may have names like anomalous discharges, charge clusters, and ball lightning. The phenomenons that seem to be shared by all the occurrences of plasmoids are the presence of strong electromagnetic fields and a current flow near the time and position of plasmoid creation. There may be a number of distinct species of plasmoids, each deriving its stability from different physical principles. These principles may involve quantum as well as quantum electrodynamic effects. It is possible that some undiscovered physical laws govern plasmoid generation. What will be done in this work, however, is to assume that at least one family of plasmoids can be described by a classical model that invokes only standard physical theory. The physical model to be presented for plasmoids may not be complete, it may have deficiencies. It may not describe, even approximately, all species of stable plasma excitations lumped under the term plasmoida. There are, however, compelling reasons to expose a simple theory based on an elementary model, which appears to be relevant to stable plasmoid creation and subsequent evolution. Pushing the theory to its limits, its deficiencies may become evident. At that point, suggestions can be made for improving the model, and where new physics has to be introduced. A force-free time-harmonic electromagnetic wave trapped in a stabilizing plasma vortical mode is chosen as a model. The functional forms of the time-varying electric and magnetic vector fields are identical, within a constant factor and phase, with this form being identical to that of the fluid velocity field of the plasma. The major electromagnetic stresses, manifested by pressures proportional to the local electric field energy, are balanced by reduced pressures due to fluid motion. The pinch effect, due to the time-varying current, adds to the stability. Using a standing wave model is not new. Kapitsa conjectured that ball lightning was explained by such a model. A model having a vortical field identical to a component of the electromagnetic field is not new either. Wells explored such a model a number of years ago. What seems to be new is the combination of the ideas to explain some aspects of plasmoid phenomena. After some mathematical preliminaries, it will be shown that time-harmonic solutions to Maxwell's equations can have the electric and magnetic fields, as well as the current in the force-free form. It will be shown that the phenomena of interest do not occur below a critical frequency, which is determined by the size of the plasmoid. Second mathematical preliminaries. A vector field, F, will be called force-free if it obeys the equation Vxf, Gf, 2, where A can be a complex-valued function of position. Unless otherwise noted, however, A will be assumed to be constant in time, spatially uniform, and real, inside regions that will be called plasmoids. Equation 1 will not necessarily be assumed to hold outside the boundary of a plasmoid. At first sight, it may seem that the only solution to EQ, 1, is F, 0. The analogy Uali brought to mind is that of the magnetic field due to a steady and uniform direct current flowing in a wire. In Fig. 1, a steady current, J, with units of amperes per square meter, is assumed flowing in an infinite cylindrical wire, producing a magnetic field H inside and outside the wire. From Maxwell's equations, Vxhj inside the wire, it is quite obvious that H and J are not parallel to each other anywhere. In general, however, it is possible to create vector functions for which EQ, 1, is true. Taking the curl of EQ, 1, inside a plasmoid results in Figure 1. Uniform current in a cylindrical wire. Beside the wire, the magnetic field is orthogonal, so the current Vxf equal to 5/5, V3f equal to a 3f. From EQ, 1, F arises from the curl of itself, so that Vf 0. Therefore, it follows that F satisfies the vector Helmholtz equation. V3 plus a 3, F equal to 0. Suitable solutions to EQ3 in spherical coordinates can be obtained from solutions of the scalar Helmholtz equation. Using the formulas 4, L, R equal to V, R, M, R equal to L, R, and N, using the formulas, where R is the radius vector from the origin to the field point. The solenoidal vector F equal to M plus N satisfies EQ. 1. Although this prescription will produce a force-free vector field for each 41 satisfying EQ, 4. It is beyond the present scope of the present work to investigate the mathematical completeness of this procedure. A concrete example of a family of force-free vector fields, MGR, 0.41, 1 plus 1, cosine. Fa, GRIA, sin, 0, 1 so. Where I is any integer, G is the familiar Spearkle-Bessel function, and the vectors I, and 4 are the familiar right-handed 3D polar coordinate unit vectors, with 0 the polar angle. The vector function MJ, R, 0, 0, is actually symmetric. That is, there is no dependence on 4 in any of the vector components, Figures Y2 to 4 show families of field lines for the solution described by EQ 8. With I equal to 1, all the points lying on a given field line define a family whose locus is the surface of a torus. If any field point approaches the radial distance, where G, R, equal to 0, the other points in its family lie on a torus that approaches a spherical overall shape, as in Fig. 4. In the limit, the field lines on the spherical part of such surfaces approach the laminar velocity field lines of an incompressible fluid flowing over a rigid sphere, with the poles being the stagnation points, 7. The I equal to 1 case will be very important in the rest of this work, since the 3 case has the highest symmetries and the smallest field line curvatures for a given radius where the first zero of G, R, occurs. An I equal to 1 spherical plasmoid will henceforth be assumed to have a minimum radius 0 rands equal to 4.493. The radius rho corresponds to the first zero of GR. At any radius corresponding to a zero off-Jeunet AR, the force-free vector field in EQ 8 has no radial component. The importance of this property will become evident below. Analytic force-free fields in toroidal coordinates have also been investigated. The name force-free came from the observation that a DC magnetic field, under vacuum conditions and satisfying EQ 1, would have to arise from a volumetric current field that was parallel to the magnetic field at every point. For such a magnetic field, the stresses on the currents, which come from the Lorentz force term P(J), where J is the current density, H is the magnetic field, and P is the permeability of the vacuum, would be nil. 4. Fig. 2. Ergodic flow lies for the vector field in EQ 8, with A equal to 1 and I equal to 1. The starting point for the flow lines is on the equator, at R equal to 4.49. The figure traced out by the lines has the topology of a torus, having a spherical outie shape with a hole along the symmetry axis. If the radius of the starting point was exactly at the first zero of J, AR, that is at R equal to 4.493, the outer shape would exactly be spherical and the hole, old, have 0 volume. This figure is viewed orthogonally to the symmetry axis, 5a, figure 3. Ergodic flow lines for the vector field in EQ 8, with the equal to 1 and equal to 1. The starting point for the flow lines is on the equator, at R equal to 3.37, about 3/4 of the distance from the origin to the first zero off JL AR. The surface supporting the flow lines is donut-shaped. This figure is viewed at an angle of 450 to the symmetry axis. Figure 4. Ergodic flow lines for the vector field in EQ 8, with A equal to I and I equal to 1. The starting point for the flow lines is on the equator, at R equal to 2.8, about 3/4 of the distance from the O-ansum to the first zero of G, or the surface supporting the flow lines resembles a thin donut. This figure is viewed at an angle of 453 to the symmetry axis, 5 billions. Since the stresses in such a system would be minimized, it follows that the energy directly associated with the magnetic field must be at an extremum. The attempt is made to utilize this principle in the design of compact toroids and spheromax. 9. In these devices, an effort is directed to produce force-free plasmategens that will have long lifetimes and thereby be hospitable for thermonuclear reactions. Force-free fields were investigated in the 19th century by Beltrami, Legge, and are still under active study. 11. Although the interested reader will find an ample literature on the subject, the non-plane wave, time-harmonic case, including self-consistent current, has not been published. Third, time-harmonic force-free electromagnetic fields. Assume the electric and magnetic fields in a neutral plasma can be written. E, R, T, E, R sin, WT plus W, and HR, TH, R SOs, WT plus phi, where W is the angular frequency of the time-harmonic electromagnetic field and I is a phase angle. Note that the fields are described by real numbers in EQs. 9 and 10. Maxwell's equations in a plasma can be written. 5xe R equal to pH, R equal to Zoc R, 5xh equal to U, R plus J R equal to R plus JR, where 1 is the permeability of the plasma, E is the permittivity of the plasma, both assumed spatially invariant, K is the wave number, K equal to VPW, and Z0 is the wave impedance, ZO equal to or 377.6 pesos ohms in vacuo. 6. If the magnetic field, H, R, and the spatial part of the current, J, R, are assumed to be force-free, as defined by EQ 1, then it is easy to see from EQ 11 that the electric field, E, R, will also have this property. From EQs 11 and 12, BR equal to GH, R, and 3, 1, R, R. If no free charge exists associated with the frequency W, then it can be shown that it is merely sufficient for HR to have the force-free form for all the other electromagnetic quantities to have this form, 3. The reason for this is that under such conditions, V, 0, and the electric field must be derived entirely from the Earl of a vector field by introducing the vector potential, A, C, E, Qs, 17 to 19, E, R, can be shown to be entirely derived from the curl of H, R, and must therefore have the force-free form if H, R, is in this form. It then follows from EQ 12 that J, R, must also have the force-free form. From EQ 12, it is easy to see that the current and the magnetic field have the same time dependence factor, COS, UT plus PP. There is a critical frequency, V, for a fixed value of A, where, and C is the speed of light in the plasma. At this critical frequency, the phase of the current changes sign with respect to the electric and magnetic fields. The significance of the last statement can be appreciated by considering the energy, Q, associated with a force-free field. From first principles, QEd plus HHdV, both E and H can be expressed in terms of the vector potential, A where ART equal to RT equal to A, R con, UT plus Y, 7, ERT, BART and H, equation 16, now becomes Q plus HVX AdV, from the vector identity. V, ax H, HVXA, AVXH, the fact that ax H equal to 0 and EQ 12, Q equal to sin 3, T plus, B, X, A R de plus, 1/2 con 32, UT plus IP, A, X, U, R plus J, R. Combining terms, 2, A, R plus, A, R minus 3, R Ds. The first term in EQ 23 is independent of time, but the second term is not, taking the time average, equal to E, R, A, R, do plus A, R minus 3, X dV. The first term in EQ 24 is always non-negative. The second term is positive for WW and negative for WV. To see this, substituting for J, R, and A, R, Ja, R, J, R, dV, equal to JR. Note that the integral is always positive, but the factor multiplying the integral goes through 0 and changes sign at the critical frequency. The second integral in EQ 24 is the portion of the energy in the electromagnetic field arising from the direct interaction of the current with the magnetic field. Since Lorentz forces on the current are 0, this part of the energy is at an extremum. This extremum represents a mininum. It can be shown that the kinetic energy density of the electrons is equal and opposite in sign to this term. See Appendix D. An interesting consequence of the phase change above AR critical frequency is demonstrated using Fig. 5. Figure 5 shows the vector potential, A and 2 currents, J and 3 plus U, all at the same point. The SIS, the current that would naturally AE, in a self-consistent, force-free time-harmonic field. Note that J is exactly out of phase with A. The current 3 plus 60 represents the original current, perturbed in such a way that the two magnitudes are equal, that is, free plumoid above the critical frequency, a Smarfel perturbation, 63, of the current, 3, will add energy to the system. 131% equal to I, 6 plus G. A perturbation such as this may arise from a local statistical fluctuation of the plasma, redirecting the current but not changing its magnitude. Since the unperturbed current and the vector potential are 180%. Out of phase and since the vector potential is not affected to lowest order by a small local current change, J plus M, a JA system, so that it behaves like an elastic body. The same logic predicts the system may 9. Be unstable below the critical frequency because a small local perturbation of the current lowers the energy. As will be seen in the next sections, stable time-harmonic force-free plasmoids may not exist below the critical frequency from several considerations. The above argumenta will be revisited when fluid velocities and stresses are introduced. Fourth, radiation and ideal plasmoids. Before discussing electronic charge carriers and the conditions for overall stability, the question of radiation can be addressed. The assumption to be made is that plasmoids will form in such a manner that the electric and magnetic fields will be tangent to the surface boundary. The rationale for this will become clearer when fluid velocities are introduced. A self-consistent, stable plasmoid cannot have a component of velocity normal to its surface. Since the velocity bell to be introduced will be identical in form to the electric and magnetic fields, the conclusion is reached that the electromagnetic fields must be tangent to the plasmoid surface. Only spherical plasmoids will be discussed, but the results are easily extended to cover possible non-spherical cases, instead of going into extensive mathematical proofs, which is done elsewhere, 13, and in Appendix A for the one case. Analogy will be made to the field inside a perfectly conducting spherical cavity excited at a transverse electric, TE, resonance frequency. In a T resonance, the electric vector has no radial component and must therefore be zero at the surface of the cavity. The condition for resonance is the vanishing of the total electric field and the normal component of the magnetic field at the cavity surface. These conditions are met by the wave number, K, and the cavity radius, a satisfying 6. G, K equal to 0, where G is the usual third spherical Bessel function. The source for the cavity celled is the surface current, ax H, at the boundary, where A is the inward-pointing normal and H is the surface magnetic field. This surface current produces no field outside the cavity. The analogy to the force-free plasmoid field can now be made. If, in EQ, 4 is taken to be either of the functions O for odd or E for even parity with respect to the polar angle 6, MJI, KR, P, C, 10, then EQs 5, 6, and 7 give vector fields R, P, con, G, KR, AP, co-80 sin, and or 1, 1, GI, KR, P, con hashtag, deg-creatine plus G, R. Matsin, consin, M8 company for a T resonance. The electric field can be written O means proportional to, and the magnetic field can be written 33. The force-free field vector derived from M can be written F plus, with a written for K. If the radius A of a force-free plasmoid is chosen to satisfy EQ 28, then both the electric and magnetic fields at the surface will have the form given by EQ 30, because M equal to 0 if EQ 28 is true. Since the field of the resonant cavity does not radiate, neither of the fields of the plasmoid can radiate. The implication is then that by choosing a radius ρ that simultaneously satisfies G ρ equal to 0 and G ra equal to 0, drastically reduces the radiation from the surface of a plasmoid. 11. The analogy between the cavity and the plasmoid is shown in Fig. 6. From now on, it will always be assumed that the plasmoids obey EQs. 35. Figure 6. Plasmoid versus cavity fides. At the surface of a perfectly conducting cavity, the electric field of a TM mode is 0, with the corresponding magnetic field spatially identical in form to the plasmoid surface fields. 5th, electronic currents. In a real plasmoid, high-frequency currents are assumed to be carried by the electrons. In what follows, the electrons will be treated like a gas, neutralized by the background of ions, as shown in Fig. 7. Difficulties will be ignored that might be encountered when the wavelength of the radiation becomes so small that it approaches the size of the Debye length. Likewise, statistical effects due to temperature will not be considered. In the absence of fluid motion, The overwhelmingly dominant forces assumed acting on the electrons will come from their interaction with the electromagnetic field. Under these conditions, the ions will represent a stay, figure 7, the neutral plasma. The electron density in a plasma will be assumed high enough to be approximated a gas, interacting with the dendralizing ions and the neutral atoms. In a plasmoid, above the critical frequency, time-harmonic current is carried by the electrons. 12. Shineri background, and will also be ignored in this section. The effects of fluid motion will be investigated in a subsequent section. Electronic motion is governed by Lorentz forces, demonstrated in Fig. 8. In an electromagnetic field, the force on an electron is m1 equal to c plus cvxh, where m is the electronic mass, f is the acceleration, v is the electron velocity, and E is the electronic charge. If electrons could exactly folio curved electric field lines, the second term in EQ 36 would be 0 in force-free fields. Figure 8. Forces on a moving electroelectric forces act on the electrons, whether or not they are in motion. Magnetic forces act only on moving electrons. As a first approximation, electrons will be assumed to execute very small amplitude simple harmony motion tangent to the field lines, with the Vxh term ignored. In that case, using EQ 9, the first integral of EQ 36 gives the velocity at ρ, v plus Ra Cos ust plus 4. This velocity can now be used to determine the free electron charge density, P. Since JPV, EQ 14 and 37 can be combined to give a minus, equation 38, says two things about PE. It calculates the magnitude and the sign of the electronic charge density. Since the sign of the charge density must be negative, because the sign of the electronic charge, E, in negative, it follows that electrons cannot carry the high-frequency current in force-free plasmoids below the critical frequency. That is, if Ca, then the current must be carried by the ions. Since the ionic mass is so much larger than electronic mass, this is clearly an impossibility, at least from a classical viewpoint. There are several conclusions to be drawn from EQ 38. The first is that self-consistent force-free plasmoids cannot form below the critical frequency. When they can form, the free electron charge density must be uniform and increases quadratically with frequency. 13. Although the above analysis directly gave the charge density by assuming the current was consistent with Maxwell's equations, and electrons obeyed Newton's laws of motion, no mention is made of stability. A full analysis of stability will have to include the effects of the electromagnetic stresses internal to the plasmoid. It will be shown later that these stresses can, for the most part, be replaced by a pressure proportional to the square of the electric belt, which can be cancelled by vortical motion in a non-relativistic approximation. The simplified analysis to be given below does not include electromagnetic stresses, or can be thought of as assuming that they have been cancelled by other mechanisms. Under this assumption, it will be shown that stability is still not assured unless the frequency and charge density are identical to those that have already been derived from other considerations. It will also be shown that small perturbations in the magnitude of the free electron charge density will cause the electron gas to contract if the magnitude increases and expand if the magnitude decreases. VL, virial considerations. Consider the moment of inertis, I, of the electrons in a finite plasmoid, and its time derivatives, 1 equal to prev, 1 to 2 par TV, and 1 to 1 to pm plus 14, where pm is the assumed spatially uniform mass density of the electrons, r is the position vector associated with an infinitesimal blob of electrons, and the integration is over the volume of the plasmoid. Strictly speaking, the integrations in EQs 39, 41 should be sums over individual electrons, but their densities are assumed high enough for the integral to be an appropriate approximation. The quantity will be called the virial of the electronic motion, 14.1.1. The exclusion of the electromagnetic field densities from the above integrals is assumed to be justified in the non-relativistic limit to deal with lowest order effects arising from variations of charge density and current. Subsequent analysis will deal with the direct 14 effects of field densities on the mechanical stresses in a plasmoid, and how they interact with the fluid dynamics of the plasma. It is assumed that, under non-relativistic conditions, these separate effects can be dealt with independently. The quantity r, z, y, z, t, is the instantaneous position of an infinitesimal volume whose mean position is at the fixed point ρ equal to r, z, y, z, equal to 2, and, to first order, merely resolates with the same frequency as the applied time-harmonic field. By definition, the velocity v is proportional to j. V equal to JPE 42, where P is the spatially uniform charge density of free electrons. The charge density, P, is simply related to the mass density, P by P, equal to EMPM, where ER equal to 1.759, 1011 cool, 9. Since all the quantities are assumed to be harmonic in time, so that J, Z, Y, Z, Tj, ZYZ, Cos, Wt plus W, then R can be written, for small oscillations about the point ρ, R equal to ρ plus JJC, Cs, Wt plus Wdt equal to ρ plus XR deg, sin, Wt plus P. 43. A necessary and sufficient condition for stability is that the time-integrated average of I is 0. This condition implies that the moment of inertia of the electron cloud can assume its original value any number of times, and cannot become unearnably unbounded as time increases. Instead of working directly with I, however, investigation will be made into conditions under which the time-integrated average of I is 0. This condition is more subtle. A necessary, but not always sufficient, condition for the time-integrated average of I to be 0 is that the time-integrated average of phi be 0. What will be shown is that if the uniform charge density has exactly the right size, and the frequency is above a critical value, the time-integrated average of R is exactly 0 if all other stresses are balanced. A larger, smaller, value for the charge density would drive the time-integrated average O phi negative, positive, leading to contraction, expansion, and ultimate instabilities. This is because the exact value of uniform charge density derived for a null is the same required from classical mechanics to simultaneously satisfy Maxwell's equations and the laws of inertia with finite Ea electrons in harmonic motion along field lines. Since other factors will enter when considering the electromagnetic field densities, the conditions to be derived will, for the charge densities, must only be considered necessary, but not sufficient for stability. Gurdjieff and Stabler, 16%, discuss a similar point. Substituting the time-dependent R from EQ, 43, into EQ, 41, and taking the time average automatically gives 0, because of the assumption that the charges oscillate with fixed centers implies confinement. It is far more interesting to substitute for the terms. 15. In I, writing Feld quantities in terms of the current, denote the time-integrated average of a quantity by to calculate conditions for stability. A bar, I, to obtain new information from OQs, 40, 41. Note that the terms in the integrand containing F, the acceleration, are related to the volume force on the electrons. 1. Pat equal to PER con UT plus 4. The term with Li 3 can be written from EQs 14, 40, 41, 43, 44, 45 and 46 with a little algebra. Hold, in order for the right-hand side of EQ 47 to be 0, the following conditions must: Ka and P me 1/6 02 minus 12, where M E 5x 10 through 13 kg cool is the mass-to-charge ratio for the electron. Equation 49 can be derived using a Lagrangian formulation. From variational considerations introduced in classical mechanics, the result in EQ 49 can be shown to arise from only assuming that the quantities E, H, and J have the force-free form, and that the free electrons carrying the current have non-zero mass. Uniform charge density is not an a priori assumption in the Lagrangian calculation. 13. 16. Besides providing the criterion necessary for stability, EQ 47 predicts the consequences of the magnitude of P deviating from that in EQ 49 If IP1 increases or decreases in size, the bracketed factor in EQ47 will decrease or increase, respectively. If this occurs in isolated regions, the bracket, naturally, cannot be taken out of the integral. Physically, the situation is diagrammed in Fig. 9. A local increase in 1p1 means that the contribution to dCi-d2 will become negative in the neighborhood of the increase, leading to the contribution to di-dt becoming negative, leading to a local contraction of the electron gas. This is an unstable situation because it will cause a deviation from force-free motion and could destroy the plasmoid. Similar reasoning leads to the conclusion that a decrease in charge density leads to a net expansion of the plasmoid. Or, Figure 9, effects of local charge perturbations. Local fluctuations in electron charge density can cause planoids to constrict or expand. Physically, this can be understood by considering the energy of self-interaction of the current in a plasmoid. Two side-by-side line currents of equal size in close proximity attract each other with a force proportional to the square of their current because the magnetic field between them has a smaller energy density than in the region outside. The magnetic pressure arising from the electromagnetic stress tensor pushes the wires together. This is also the origin of the pinch effect in plasma physics. Increasing the free electron charge in a plasmoid will increase the current, leading, qualitatively, to a volume pinch effect tending to contract the volume of the plasmoid. Similarly, decreasing the charge density decreases the pinch effect and leads to expansion. This increase, contraction, decrease, expansion seems to be an inherent instability of a plasmoid where statistical fluctuations of charge density might occur. Any local increase in charge density, causing a contraction, would tend to compress the region, making the free electron charge density increase even more. Similarly, for the decrease expansion case, this positive feedback is countered by the tendency of an ionized plasma in a strong electromagnetic field to have its radiative recombination rate increase with density and its ionization rate to decrease with density. Statistical fluctuations in charge density would then be nullified to some extent by ionization recombination processes in real gases. A full calculation investigating this phenomenon has not been done as yet. The sensitivity of the ionization recombination rates to gas density as a function of frequency and electric field amplitude may be a crucial factor in plasmoid stability. As was already mentioned, the conditions in EQs 48 and 49 are necessary for stable. 17. ITI. If all other stresses are absent. The added condition that makes 48 and 49% sufficient is that d7y equal to 0, since equations 48 and 49 are the conditions also derived from solving Newton's laws of motion for the plasmoid system when the electromagnel 3/4 SE stresses are ignored. Since the fields are stationary in space and time, except for the harmonically oscillatory part, it follows that at t equal to 0 the plasmoid initially has di-dt equal to 0, where the t in EQ 44 is time for a single cycle of the oscillatory field, t equal to 27 Rw, ignoring electromagnetic, thermodynamic and fluid stresses, EQs 48 and 49, constraining the frequency to be above a critical minimum and the free electron charge density to be uniform, and a specific quadratic function of K and A, represent necessary and sufficient conditions for plasmoid stability. In the next section, electromagnetic stresses will be discussed in more detail. Unless these stresses are balanced, they will tend to make the virial of the electronic motion, I, positive. In other words, the electromagnetic field trapped in a plasmoid acts like a positive overpressure, tending to make the plasmoid expand and dissipate. A mechanism will subsequently be discussed that will balance out all but a very small part of the electromagnetic stresses. 7th, electromagnetic stresses. The usual analysis involving the virial theorem, 14 feet energy density in the integrand in EQ 39. The assumptions made here are that the electronic velocities are non-relativistic and the harmonic fields E and H are non-zero inside the plasmoid and do not have the force-free form outside. It is possible to have an external time-harmonic field that obeys free space conditions with no discontinuities appearing at the plasmoid surface. The external branch of the electromagnetic field has no currents, does not have the force-free form, and will be assumed to have no stresses associated with it. 1 second 1617 includes the electromagnetic. It is important now to estimate how close a real physical system can be made to approach the conditions for force-free field approximations on the vector fields, EH and J. If electrons were massless, the problem would be far simpler, since they would experience no centripetal accelerations and would conform to electric field lines like currents in wires. In reality, the electrons cannot confine their motion to be strictly along the curved field lines of a force-free field. The assumption that the electrons undergo simple harmonic motion along electric field lines becomes more accurate as the frequency increases and the electric field decreases. This can be seen from EQ 43, where the amplitude of the harmonic motion is J, pu. Substituting for in terms of E, a condition for small amplitude oscillations can be written 18, rho 50. Where Lmar is the maximum absolute amplitude of the harmonic electric field within an I1 plasmoid and ρ is the radius. Using RMKS units EQ, 50 becomes Elms equal to 2.02 x 10 volts M51, where is an appropriately small factor that satisfies EQ, 50 and A is the free space wavelength of the harmonic wave. While EQ, 50, gives a criterion for small amplitude electronic motion, a more exact expression can be written for the forces on individual electrons in a force-free time-harmonic plasmoid. When these forces are known, trajectories may then be calculated, and an assessment can be made of techniques for balancing the forces. It will be shown below that the condition in EQ 50 is related to the problem of electron drift in a plasma. That is, in this context, the tendency for electrons to move orthogonally to electric and magnetic field lines. The approach will be to expand the acceleration field as a perturbation series about the harmonic motion. For purposes of perturbative expansion, it will be assumed that the frequencies to be encountered will be high enough, and the respective field amplitude small enough to say that the major part of the electronic velocity will be harmonic motion along electric field lines defined by solutions to EQ1. Since the field lines have curvature, these oscillations will be accompanied by a drift motion across electric field lines, as in Fig. 10, unless the effects of the curvature are balanced by some other mechanism. There are several reasons why this electronic drift is undesirable. First, as shown above, the current in an ideal force-free plasmoid will not radiate under the right conditions of size and frequency. Drift currents, not having the force-free form, are capable of radiating, potentially unbalancing the plas. 19, Figure 10. Drift due to field curvature. If the field lines are curved, the electrons will continually drift, toscillate along different field L-moid mechanically. Next, drift currents may have a divergence that would lead to a change in charge density if the rest of the plasma were not present. Since the plasma creates large restoring forces to maintain neutrality, drift currents can be responsible for pressure gradients that could disrupt the symmetry of a plasmoid, causing its self-destruction. In any case, drift currents may have non-linear effects that can build in an uncompensated manner and tend to shorten the lifetime of a plasmoid. It is important, then, to understand the regions and dynamics of drift currents. Toward that end, the forces acting on the free electrons will be examined in detail, assuming non-relativistic conditions. An electron is acted upon by the Lorentz force, F equal tom J equal to EE plus XB 52, where B equal to AOH and R is the instantaneous position of the electron. Instead of an analysis of EQ 52, that will relate the components of F to elements of the electromagnetic stress tensor 20. The drift motion will be taken as a perturbation determined by the oscillatory motion along electric field lines and the curvature of the components of the field gradients. The connections to the stress tensor also will be discussed below. It will be assumed now that the frequency of oscillations W is so high that in the time needed for one full cycle of the electric field, T equal to 2 rho W, the net motion of the center of mass of an electron oscillation is very small compared to the overall size of the plasmoid. This slow net motion can arise because of field inhomogeneities in the B and E vectors, as well as the relative local orientation of B and E. The major electronic motion, then, over many cycles, will be high-frequency oscillation along local electric field lines. This high-frequency motion will be superimposed on another component, whose net effect would be to slowly transport electrons onto different electric field lines. The following analysis closely follows the logic on pp77 to 80% of Gecker's book. 21. Assume that the position vector r may be written as a sum of an oscillatory term, RL, and a net transport term, ρ0. Let the oscillatory term arise from ignoring the magnetic field's contribution to EQ. 5, 2. It then follows from EQs 9 and 10 that ρ equal to 7w to 2 E rho t cos plus 5, where Q equal to EM equal to 1.76 ac 101 col kg, the ratio of the electronic charge to its mass, and the electric field is calculated at position ρ. The quantity ρ takes into account only the 53/20 straight line motion tangent to a felled line. After the contribution from RE is added on, the trajectory should contain all the corrections for curvature. Equation 52 can be rewritten. F plus equal to E plus 1, 1, plus N, T plus H, X B, X plus 8, F. Expanding the right-hand side of EQ 54 as Taylor series in R1 and rearranging. FO plus equal to RT plus N 5 E rho plus N to 5 3 E RT plus VTOX B rho F plus R 5 B rho F plus N5 3B N1 plus Nix B RT plus N5 B RT plus R 5 3BR plus, subtracting the second time derivative with more rearranging. The equation for 2 is Toma R5 E rho 1 plus XXB rho 1 plus 5 plus to X B rho F plus N5 B rho F plus 5 R plus R B R F plus X from Maxwell's equation VXE. 0 billions per 0 trillions EQ 53 and the familiar vector identity VAB equal to A. VB plus B VA plus AX VB plus BX VA EQ 56. I R V2E rho T plus 1 plus 121 1 B ρ0 T plus R VB rho T plus 2 RB ρ0 T plus 57 VB rho T plus 1 R B's road plus I. The first term 6 and the right in EQ 57 can obviously lead to gross motion of the center of mass of an electron. It says that the electromagnetic field can produce a volume stress in plasmas that appears to arise from a pressure proportional to the square of the electric field D and inversely proportional to the square of the frequency. Many of the other terms in EQ 57 lead to oscillatory motion with no time-averaged velocity of the center of mass. To lowest order, assume that the oscillatory part of I. Then, since ρ and E, ρ, both have sin, Wt plus W dependence, the first higher-order term to contribute a non-zero time-averaged contribution in the first square bracket is T6, R, V, 3E, ROT, with sin 4, Wt plus P, appearing as the time dependence. Similarly, the first higher-order term to contribute in the last square bracket is 1, IL-X, RLV 2 billions, T, with sin 2, Wt plus P, cos 2, Wt plus P appearing. To lowest order, none of the terms in the second bracket can contribute to non-oscillatory motion because B rho has COs, Wt plus P dependence. The electric field must now be restricted in size, not only to make the series in EQ 57 converge, but to prevent the higher-order terms from making a substantial contribution to the motion. A physical restraint will be that the maximum value of ρ be much smaller than 0 rands. From EQ 53, define a small parameter, C very similar to sin EQ 51, where equal to less than 1, 58, 22. I am equal to Note that for fixed values of E and Ka, W is inversely proportional to Re, and the maximum electric field intensity varies inversely with plasmoid radius. Maximum energy densities can therefore be inversely proportional to the square of the radius without violating stability criteria. It Cn then be shown that the time-averaged force on an individual electron can be written 1 MeV equal to 4511 Pliu SJC. In the next section, it will be shown that EQ per 60 produces an effective non-uniform fluid pressure proportional to the energy density in the electric field. By introducing vortical motion, variations in the total time-averaged fluid pressure governing the flow within the plasmoid will be cancelled to order C2. Field vortical plasma stabilization. The time-averaged volume force on the electron fluid at any point is LA, FV equal to 7 from EQs 38 and 16, FV equal to I, L, EV, RJ2, J plus 0, 42. To order C2, this is equivalent to the volume force that would arise from the gradient of the pressure field, P, R, equal to JQS22, E, R12 plus PO, 23, where P is a constant that may not be 0. A great deal of care must be taken to account for all the stresses due to the electromagnetic celled. Equation 57 is correct throughout a region where all the quantities exist and are analytic. It is important to note that the approximation, EQ 63, derived from EQ 57, is not what can be derived from a localized interpretation of the meaning of the electromagnetic stress tensor in a plasmoid. This subtle point is worth exploring in a little more depth. The electromagnetic stress tensor in a homogeneous isotropic linear medium, 3S, is physically defined by its divergence, V, 3S, equal to V xe plus RVE, plus 5xh, xh plus hvh, which can also be expressed in the form fifth 2s equal to pe plus jxh, where pe is the net free, unneutralized, charge, and j is the current. In an ideal force-free plasmoid, there is no free charge, p 0, and by definition, jxh equal to 0. The divergence of the electromagnetic stress tensor is therefore identically zero there. Where trouble can arise is in writing an expression for the stress tensor having the dyadic form, S equal to E, epi, plus HH, where I is the unit dyadic. It is true that, integrating over the volume and surface area of a plasmoid, PE plus JXH, DVL 18 ADA, where A is the outwardly pointing normal. Obviously, the integrals in EQ 67 are equal 0 for a force-free plasmoid, to 24, to S.FIE, IFI, Fun J12F plus P, H-Phi, 1IH 126. The usual interpretation of the quantity in EQ 68 is that of a local stress being communicated across the surface of integration. See Fig. 11. In this case, since both electric and magnetic fields have no normal components at the surface of the plasmoid, the electromagnetic stress, from EQ 68, amounts to a pressure equal to the total energy density of the electromagnetic field. In reality, there is no local net force in an ideal force-free plasmoid. The analysis done to find the pressure due to Neu-Mars electrons finds a quantity in EQ 63 that differs at the surface of the plasmoid from assuming strews to arise from EQ 68. Even though, as the frequency increases, with the size off the plasmoid fixed, the differences become smaller, EQ 68 cannot be used and has no relevance to the local pressure field when the fields are assumed to be from the force-free solutions to Maxwell's equations. Relevance can be re-established by allowing plasmoids to have different fields directly inside and outside their boundaries, forcing currents to flow on their surfaces. These currents, a single layer needed for the jump in the H field, and a double layer needed for a jump in the E field, will hit a reaction to the fields at a plasmoid boundary that will effectively act like an outward local pressure proportional to the local energy density of the electromagnetic field. Within a constant factor, this latter pressure has the same functional form as the first term in EQ 63. As will be shown below, the pressure represented by the first term in EQ 63 can be balanced by a vortical motion of the fluid in the plasmoid. If extra stresses occur at the surface, they can be balanced by modifying the magnitude of the fluid velocity everywhere. This would, however, unbalance the stresses everywhere else in the plasmoid. In a perfectly non-viscous fluid, it would also be possible to modify the velocities found in the outermost toroids of the vortical flow to compensate for the stresses surface currents would produce. Since the flows in separate toroids of the vortical motion are independent, the rest of the plasmoid would be unaffected. It is easy to see that even in the absence of viscosity taking. Figure 11. The stress tensor. The Oumuamua interpretation of the stress tensor translates to a local S2AAUF 25. Surface currents into account complicates the theory. In the next section, it is shown that some or all plasmoid surface currents can be eliminated if special external cells are present. It will be shown that these external fields can be described by the resonant modes of a perfectly conducting spherical cavity. In view of this, the theory will now be developed ignoring the effects of surface currents. Even though the gradient of the pressure field in EQ 63 acts only on the electron fluid, it is transmitted to the ions via the electrostatic forces that NCRC quasi-neutrality in the plasma. The internal flow of the plasmoid will then be governed by static and dynamic fluid pressure gradients, in addition to the forces in EQ 62. In what follows, it will be assumed that the plasmoid behaves pseudodynamically like a perfect gas, with constant thermal conductivity and specific beats. A flow field, with velocity distribution VR, will now be introduced that counteracts the pressure in EQ 63. Let V R equal to AMR, where A is a constant to be determined and M R obeys EQ 1. In other words, the streamlines of V are identical with the harmonic electric field lines. This steady flow field is potentially stable, as can be seen by applying the equation for the evolution of vorticity, AM L Vx Vx equal to AV. In EQ 70, the right-hand side is identically 0 because V has the force-free form, with VA multiple of VXV force-free vortices, with vector celled MR, are not the only candidates for stable motion. If the vector function, Vx, is the gradient of a scalar function, the vortex formed by the velocity phi is also potentially stable. Hill's spherical vortex is in this latter class. Exactly equivalent to EQ 70 is the expression for the rate of change of, in an element of fluid that is convected with purely vortical flow, dj dt jw from EQ 71. This becomes 26 dt. Since V has the force-free form, the formula for the gradient of a dot product of two vector fields implies 5 if Equation 74 says that the acceleration of an element of fluid moving in a force-free vortex can be derived from the gradient of the square of the velocity. Multiplying both sides of EQ 74 by P, the fluid density, and assuming uniform density, dV1 dt equal to 2 VPLVL, it follows that the volume force on an element or fluid in a force-free vortex may be thought to arise from the pressure field. 1-2 PV equal topo, PLVL 2, where PO is a constant and P is spatially invariant. This pressure can be adjusted to cancel the major part of the electromagnetic pressure. It is immediately obvious that the value of A in EQ 69 should be, where the spatial part of the electric field is EOM-R, the above analysis leading to the result that vortical motion can cancel the major portion of the electromagnetic forces on the electronic fluid, leaving only a uniform residual pressure. 0 pesos everywhere is so important that it will be derived in another manner. Some assumptions will be made first. 1. All processes are adiabatic, so that the specific entropy is spatially uniform. 2. The gas pressure, P, must equal the surrounding ambient pressure. 27. 3. The gas density, P, must be uniform within the plasmoid. Any flows that are incompatible with any of the above assumptions will not be considered. Before going ahead with the alternate derivation, these assumptions should be discussed. Assumption 1 says that all fluid motions were initiated without the addition of heat. Also, no processes occurred that generated or transferred heat. If the plasma in the plasmoid was derived from the surrounding plasma, then the specific entropy of the plasmoid is equal to the specific entropy of the surrounding plasma. Assumption 2 says that the only pressure gradients that can remain in the plasmoid after the vortical motion cancels the electromagnetic pressure must arise from the thermodynamic gas pressure. Assuming an atmosphere surrounding the plasmoid exerts an isotropic pressure P, the internal thermodynamic pressure must match this for stability, after surface current effects are included. In large systems, P will probably arise from the surrounding gas pressure. In small systems, there may be a component of pressure from a Casimir force. Casimir forces will arise in situations where, owing to the Lie conductivity of the plasma due to large numbers of free electrons, components of the electromagnetic zero-point background energy cannot penetrate uniformly into the plasma. This will result in a lower area density within the plasmoid and an apparent pressure gradient due to the vacuum. It is beyond the scope of this note to investigate zero-point effects. Assumption 3 must hold in order to allow the forces that arise from vortical accelerations I.O. be derivable from a conservative field. The key to the alternate derivation is the understanding that the specific internal energy of the plasma is a sum of the perfect gas thermodynamic specific internal energy, C, and the electromagnetic energy density per unit mass of fluid, Q. The thermodynamic quantities are equal to C, co T, 78, where S11, C and T are the epicycle C heat at constant pressure, the specific heat at constant volume, and the temperature, respectively, from EQ 24. The part of Q that is affected by the fluid flow is represented by the term with J in it, since the current can be transported by the fluid flow. Using this logic, an effective energy density can be written, IT equal to A E I L I'm R2 79, with A and J defined in CI 28. Mont. Bernoulli's Theorem 7 now says that along every streamline the following physical quantity is conserved. S2 plus E plus, since Q is 2 negative, Ka, the logical choice. V equal to AM, R, where A is defined in EQ 77, will exactly cancel out the electromagnetic stresses in EQ 63. A result already derived to within order C2. This discrepancy to order C2 might have been expected, since the higher order terms arising from the curvature of the fields, in EQ 57, were ignored. In the above proof, using Bernoulli's theorem, it is assumed that the electronic current is convected by the fluid motion. Since the fluid motion is assumed to 1e, a purely solenoidal mode, no compression takes place, and the electronic density remains uniform. Under these conditions, it could, alternatively, be assumed that the electrons, and thereby the currents, are not convected by the fluid, with only the ions and neutral atoms participating in the fluid flow. In this case, Qg will not appear in EQ 80, but the pressure due to the electronic motion would still be transmitted to the ions and would have to be subtracted from the pressure P in EQ 80. It is then easy to see that exactly the same velocity profile would have to be assumed to balance the electronic contribution, whether the electrons are convected with the fluid or not. From simple energy considerations, it is more likely that electrons are convected with the fluid, there would then be no external static magnetic field due to the motion of the ions. The kinetic energy of the electrons is ignored here. A full analysis would have to compare the added kinetic energy due to electronic motion to the energy in the magnetic field that would arise if the electrons were not entrained. It is assumed here that the electronic kinetic energy would be smaller, with the first two terms in EQ 80 cancelling the quantity 6 plus Pc, cancelling the specific enthalpy is constant along any flow line. It immediately follows that the temperature must be constant along a flow line. If the motion of the compressible gas is to remain steady, then the pressure must be constant in the plasmoid and assumed equal to 29, the pressure of the ambient atmosphere. This, then, forces the mass density, P, to also be a constant within the plasmoid. Since pressure, density and temperature are constant throughout the plasmoid and may take on the same values as in the ambient isentropic atmosphere, the flow is isentropic and therefore can be initiated by an adiabatic process. The criteria of the flow, listed as assumptions 1 to 3, above, are met. As field strength increases, the fluid speed from EQ 77 must increase in the same proportion. The question naturally arises as to whether turbulence will occur beyond a threshold velocity. This cannot be answered in full, but if the electrons are entrained in the flow, there is a mechanism that will resist small perturbations that may grow into turbulent flow. Remember that the term Q equal to 1/2 pJa, which is proportional to the time averaged energy of interaction of the magnetic field and the current in the time harmonic field, is negative for Ka. A small perturbation in velocity that does not change IVI, but I implies a local change of flow direction without changing A, will decrease the magnitude of Q. The reason for this is that the entrained current will still have the same magnitude, but its component parallel to the original direction, parallel to a must be smaller. A smaller magnitude of Q means increased energy, which leads to a restoring force proportional to Tesoro 12. The fluid therefore would appear to become more rigid as the field strength increases, at least patously offsetting small statistical fluctuations that could grow turbulently. This effect has already been mentioned in association with EQs 26, 27, and Fig. 5. Note that a force-free vortex cannot occur by itself in a compressible fluid. The pressure gradients would immediately give rise to velocity components that were not solenoidal. Such a situation would lead to rapid destruction of the vortical field. Similarly, a time-harmonic force-free field cannot persist by itself in a compressible fluid because of the stresses due to finite mass electrons in the presence of electromagnetic fields with non-zero curvature. The remarkable coincidence of force-free vortices being stable in the presence of force-free electromagnetic fields makes the entire theory viable. There is a very special case that is worth mentioning, even though the possibility of its physical existence may be apocryphal. At the critical frequency, where W equal to Ca, the current and charge densities become zero, it follows that a force-free electromagnetic excitation cold exists in otherwise empty space. The energy would be contained within a spherical region, terminated by a set of boundary currents, and could not radiate away. Classically, there is no limit to the energy density that might be confined in such an electromagnetic mode if the outside influences are E large enough to contain the stresses on any surface currents that would be needed to match boundary conditions. If such an object could exist, the limit on the field strengths would be near the point where the vacuum polarization due to virtual electron-positron pair production was affected. Classically, such a vactoid, vacuum plasmoid, would be almost undetestable. Assuming the correct terminating currents, the electromagnetic fields immedi, 2 outside. 3O. Its boundary are nil, and no charges inside it are present to radiate. A more modern view says that the trapped energy represents an E equal to mc2 mass and would have a gravitational field. Also, scattering from virtual electron-positron pairs might eventually lead to decay. Unless there was a direct contact with ionizable or charged particles, the presence of an individual vactoid would go unnoticed. The interaction of two vactioids, or, for that matter, two force-free plasmoids, is not yet known, but can be investigated. The major argument against the existence of vactioids is the apparent need for a set of surface currents to match the inside-to-outside boundary conditions, with no mechanism to generate or support them. The Lorentz forces on such currents would amount to a pressure equal to the energy density of the electromagnetic field at the surface. This would tend to force the vactoid to disperse unless there were processes outside the vactoid that balance the electromagnetic pressure acting at the surface from the inside. Even apart from this vacuum special case, a reliable process for manufacturing force-free plasmoids is still to be found. In the next section, some of the issues involved will be discussed. Appendix B discusses the case Ofan Enigdic, 1 megajoule, 20 centimeters, diameter plasmoid formed in air at sea-level atmospheric pressure. D1. Discussion. The analysis so far has assumed that force-free plasmoids exist and proceeded to derive some of their properties. This was taken to be a worthwhile intellectual exercise, since the theory appears applicable to otherwise unexplicable observations. As it stands, the weak points in the theory concern prescriptions for the manufacture of force-free plasmoids and the nature of the fields external to, yet compatible with, force-free plasmoids. These last two issues lead to the suspicion that describing autonomous self-confining energetic plasmas, such as ball lightning, with force-free fields is probably not incorrect, but may be incomplete. This section aims at disusing the previous sections, highlighting some of the shortcomings of the theory. Arguments found at the end of SEC 3 accompanying EQs 28-35 were used to show that the fields at the surface of an ideal plasmoid do not radiate. No inferences were made about the transition in field amplitudes at the surface of a plasmoid. The moot point as to whether there can be a true discontinuity in each, or either, of the electric and magnetic fields between inside and outside the plasmoid will not be considered in great detail. If a true discontinuity can arise, the question of how to determine surface currents cannot be answered easily. The assumption will be made that if there are discontinuities that transition to the outside, fields occurs continuously. That is, there must be a small region in the neighborhood of the boundary of a plasmoid where the fields, along with their Fourier derivatives, change continuously. If so, then plasmoids must have currents in this region to match the boundary conditions imposed. 31. By classical electrodynamics, if not, the possibility that plasmoids may exist having no surface currents must be investigated. Lack of surface currents leads to the apparently illogical consequence of a standing wave having no sources. As an approximation, however, this may not be an impossible situation. There may be waves whose space-time symmetry severely limits their ability to propagate in the usual manner. These waves do have sources, but the compact support of these Gausses may be a very complicated function of the retarded fields. In the literature, such waves have been called diffractionless, phase-conjugated waves, electromagnetic missiles, Bessel beams, etc. 3. A force-free plasmoid, unterminated by surface boundary currents, may fall into this category. The rate at which a plasmoid disintegrates if no boundary currents exist be investigated. As has been seen, these currents are needed to satisfy Maxwell's equations, but since they do not radiate, they are not needed to counteract a steady-state flow of energy from the surface of the inside region. To make the last point clearer, consider the case of three-dimensional space divided into two regions, inside and outside, by a spherical boundary. On the inside, for r rho the electric and magnetic fields are E, and H. On the outside, for r rho, the fields are E and H. If A is the outwardly pointing normal, it is shown in standard texts 3 that the inside and the outside will evolve independently if the surface, at R, equal to rho sustains the equivalent electric, J, and magnetic, M, currents, J acts, H, M, equal to X, E. For solving problems on computers, the carriers of these currents are irrelevant. Physically, I can be carried by normally charged particles like electrons. The magnetic current M can only be approximated by normally charged particles, since magnetic charges evidently do not exist. The purpose for this discussion is that if a real steady-state, force-free plasmoid were to exist, with non-zero fields inside and free fields outside, some mechanism would have to be provided to sustain multiple layers of sheet currents on the surface of the plasmoid if there are discontinuities in the fields. No such mechanism immediately concedes to mind. On the other hand, assume a plasmoid of this type is suddenly created with no surface currents. The jump conditions at the surface can initiate a mode of disintegration that involves transient. One suspects non-harmonic phenomena that will generate waves whose initial energy densities can be equal to the electromagnetic energy densities at the surface of the plasmoid. These waves would linearly add to the fields inside and outside the original. 32. Plasmoid. Since they are free space waves, these transients would not by themselves disrupt the internal plasmoid fields. Very quickly then, the space around the original, now decaying, plasmoid would fill with ultimately outgoing energy. The exact form of the outgoing radiation then, in principle, can be calculated. It may then, in principle, be possible, knowing the outgoing field quantities on a fixed surface, to establish an externally generated electromagnetic field that can set up a standing wave that exactly compensates for the losses at the surface of the decaying plasmoid. A model like this is very close to that described by Kapitiza, 4. Surprisingly, the spherically symmetric form of all the assumed fields allows straightforward analytic solutions that permit plasmoid properties in a spherical region 0R no. Standing waves in the outer region are less than or equal to U, and do not require any currents on the surface at R equal to R. This situation is graphically shown in Fig. 12. In Fig. 12, the region 0ρ contains a force-free harmonic plasmoid at frequency W with fields and currents obeying EQs. 9.14. The spatial part of the fields in this region are assumed to be proportional to m in EQ. 8. Since a ρ is a zero of the Bessel function g, r, the fields on the Sirfeld's face of the plasmoid are directed along the polar 6 direction. Are parallel and tangential to the surface. This can be exactly matched by external vacuum figure 12. Ticks. At Selda, matching plasmid boundary condi the surface of a plasmoid the E and. In addition, R equal to R is a zero of G, K, R. As a consequence, the magnetic field of a TM cavity mode at frequency W can have its magnetic field equal to 0 at R re, and its electric field will only have a component. The dual situation of a T cavity mode can have its electric field equal to 0, and its magnetic field will only have A and component. It is a simple matter to adjust the amplitudes of a TM and a T mode so that all the fields are continuous at re. There is then no need for currents at R equal to Rs, but a need to maintain an external electromagnetic field with the correct boundary conditions. In principle, this can be done without violating any physical laws. Alternately, a plasmoid could be created with a single layer of electric current on its surface, which would allow a surface discontinuity in the magnetic field. To obviate extra layers of current, the external standing wave field can be a pure TM cavity mode with zero magnetic field at the surface of the plasmoid. The boundary conditions for such a situation are, in principle, achievable inside a conducting spherical cavity, as shown in Fig. 13. The radius of the plasmoid, R1, satisfies EQ 35, while the radius of the cavity, A, is chosen to satisfy Saj, Kr, all 1, equal to 0, as can be seen by examining EQ 31. The latter problem is to create and maintain a single sheet of surface current to neutralize jumps in the surface magnetic field proportional to CSK less than 1 CEQs. 11.13. This seems more tractable compared to generating and maintaining a double layer of extremely large currents to match a discontinuity in the electric field. The magnitudes of these large currents would have to be inversely proportional to the skin depth or transition region between the inside and the outside of the plasmoid, and would have to be out of phi with each other to simulate a discontinuity in only the electric field. As result, the two sheets of current would strongly repel each other, tending toward instability. Figure 13. Matching plasmoid boundary conditions in a resonant cavity. By matching only the electric field at the surface of a plasmoid, a current A(J) is needed to account for the nominal jump in the magnetic field. The general question of terminating the surface of a plasmoid probably cannot be answered easily without more work. Anecdotal evidence seems to indicate that the autonomous plasmoids responsible for ball lightning do not have external supportive fields that need to match stringent boundary conditioners. 2. But measurements are virtually non-existent. On the other hand, workers in Japan have produced plasmoids with exceptionally long lifetimes in cavities sustained by microwave generators. Whether either of these examples can be described by force-free time-harmonic waves remains to be seen. In Appendix C, speculative terms are added to Maxwell's equations that would allow for a jump in either the magnetic or the electric field at a surface, without the need for a current on that surface. Apart from surface boundary considerations, a picture emerges concerning the description of a spherical plasmoid with a trapped electromagnetic field inside it, consistent with a current given by EQ 14, and an electric field given by EQ. 9. The plasmoid will have the complex capacitive conductivity, K21. Ionization levels throughout the plasmoid must be such that the free electron density is 34. Given by EQ, 49. From a practical point of view, the plasmoid can be thought to be a linear system responding to Ohm's law in the form J equal to A, WE, where J and E are complex. In EQs 9 and 10, the sine and cosine functions could have been replaced by the complex exponential EA, making E and H complex functions. Taking the real parts of these functions would then give the same physically meaningful results derived using real trigonometric time functions, M, in the high-frequency limit, K, plus CO. A plasmoid has the asymptotic specific capacitance equal to the vacuum permittivity EO, equal to 8.89 pF. At high frequencies, this is equivalent to a low impedance, meaning that high field strengths might be required to initiate small energetic plasmoids. Alternatively, the plasmoid could be thought of as a lossless dielectric material. From EQs 12 and 14, this material would have an effective permittivity, A2K2. Note that it is possible that F-phone AO, implying a superluminal phase velocity within the plasmoid. The plasmoid region will have internal vortical motion that will cancel the tendency L, expand due to electromagnetic pressure. A remarkable accident may therefore exist in nature wherein a non-propagating electromagnetic field and a special vortical fluid field with the same functional form, neither of which could exist separately, can combine to producing a long-lived, high-energy density plasmoid. The outer supportive field, since it can exist in a vacuum, would have no need for vortical material motion for stability. No radiation can escape from the surface of the plasmoid to first order at the frequency W. Radiation may occur at harmonics of W due to the oscillatory motion described by EQ 57. This radiation may have a detectable, distinct, but perhaps not unique, signature. To produce the plasmoids described in this note, the following steps must be included. 1. Closed spherical vortices must be produced. 2. Desiredly, else of ionization must be maintained. 3. Electromagnetic energy at frequency W must be produced within the plasmoid. 35. An explanation is needed for 3 above. The function being called M-R in this note corresponds to a sum of the functions M and Ni1 on pp 416 to 417 of Stratton's book. On page 419 of the same source, a plane wave polarized in the x direction, propagating in the z direction, is expanded in the form Ks000 N2 plus on ASEC, 2N plus on ENO. None of the terms on the right side of EQ 85 can contribute to the fields in the plasmoids described here. That is, the terms in EQ 85 have the wrong spatial symmetries to contribute to the plasmoid fields. The same comments can be shown to be true if the field due to a point source was considered. As a result, external localized sources, which may be expanded in terms of plane waves or point sources, cannot produce energy that will be trapped in a plasmoid. If, however, the plasmoid region was traversed by a column of current whose axis was parallel to the axis of the plasmoid, the field of the plasmoid can be pumped. Another way of looking at this is that a circular cylinder of current, with its symmetry axis coincident with the plasmoid axis, will emit radiation compatible with being trapped by the plasmoid. From what has been derived in this note, a possible scenario can be envisioned for the creation of a spherical plasmoid. A very strong discharge occurs in an ionizable gas in the presence of a high-frequency electromagnetic field. The pinch effect, due to the discharge, initiates a compression, which turns into a swirling vortex. At the right level of ionization, the external time-harmonic field is expelled from the vortical region and radiation from the column of the discharge inside the vortex at the same frequency as the external fields cannot escape. At the end of the discharge, a highly energetic plasmoid emerges that has nearly as much kinetic energy as internal electromagnetic energy. Created in a quiescent ambient gas with a low kinematic viscosity, the plasmoid will slowly come up to a speed that is compatible with its tangential gas velocity. At early times, the plasmoid could appear to move very slowly and may respond to ambient gas flows. Catastrophic demise can occur if the radiation does not leak away at the same rate the fluid motion dissipates heat via viscous forces. The fluid and electromagnetic forces will not balance, and the plasmoid may come apart. On the other hand, variations in the external fields could cause boundary mismatches that might also lead to catastrophic decay. Alternatively, the viscous dissipation may closely match the electromagnetic lows, and if thermal stresses are not too large, the plasmoid may expire gradually. The assumption will be that the smaller the value of C in EQ, 5.1, the longer the lifetime of the excitation, all other things being equal. At this time, there are no estimates for lifetimes, but some reasonable values for the parameters might be ρ equal to 10 centimeters, A equal to 1 millimeter, and C equal to 0.1. Under these conditions, a 10 centimeters radius spherical excitation may have a total energy density on the order of tens joules mi. This value is larger than average reported energies of ball lightning, 2 feet, and these excitations may represent an electromagnetically excited fluid state that could serve as a model for ball lightning-like phenomena. If C is kept constant, the total energy in any spherical excitation will be proportional to the factor Frod 86. This implies that for a fixed ratio of the radius to the wavelength, for the same value of C, the energy content of a spherical excitation is linearly proportional to its radius. Since the volume is proportional to the cube of the radius, the smaller the sphere, the higher the energy density, under the above fixed ratio of radius to wavelength. For the numerical example already given, if the radius was shrunk to 1 millimeter, the total energy content would be about 15,000 joules. The wavelength of the harmonic wave would be 10 pm, and the energy equivalent to a 50-watt light bulb burning for 5 minutes. 37. Appendix A. The equal to 1 far field. In this appendix, the far-celled radiation from the surface of an ideal force-free plasmoid will be analysed for the one case. It will be shown that, for appropriate values of ρ, the radius, the cells at the surface of the plasmoid will not radiate, even if the plasmoid is not terminated by surface currents. An important conclusion is that under certain conditions surface currents, which are needed to satisfy Maxwell's equations if field discontinuities occur at the boundary, are not needed to prevent steady-state radiation from a 2 force-free plasmoid. Let the Weaver number Beckper, E, with c being the speed of light, and w the angular frequency of the fields. Referring to Fig. A1, the Stratton-Chu formula on page 467% of Stratton's book, for the electric field due to the radiation from the surface of a closed region can be written. Figure 1. The plasmid far field. Radiation the surface with a Green's function linking the SAR from a plasmid involves integrating the field's overface with the far field point RER equal to F x R R dar plus 5 XF ax R 1 word R, where A is the outwardly normal to the region, R is the vector distance from a fixed origin to the observation point, is the vector distance from a fixed origin to the integration point on the surface. The harmonic time dependence of the field quantities is E, and the Green's function is equal to 4, 6. At the surface of a plasmoid, the fields have no components normal to the boundary, 38, so that the last integral in EQ, a 1, is 0. Since E and H are identical within a constant factor, only the first integral in EQ, a 1, has to be evaluated. It will be shown that the value of this integral is also 0 if the radius is chosen correctly. Showing that this integral is 0 in the far field is equivalent to showing that the term involving the second integral is also 0. The curl of a null function is 0. The strategy will be to first show, rigorously, that the value of the first integral, call it vi1, can be zeroed in the far field, I, in Fig. A1, arco the quantity, where r equal to r is the unit vector in the direction of r, and an angle 7 is defined by 1 equal to 0, 0, 0, 0. Now define an equivalent surface current, J, where J, ax, H. The integral to be evaluated becomes, in EQ, a A6. The integral extends over the entire surface current distribution. In the 11 spherical plasmoid case, this equivalent surface current at radius ρ can be written as a vector function proportional to, where J ARs equal to minus 2172, corresponds to the value at the first zero of G, R. The first zero was chosen arbitrarily. Any other value of R for which J, AR, equal to 0 would give the same result. The value of 5 becomes proportional to the integral. Where the distribution is centered at R equal to 0, standard spherical coordinate notation is used, and the integration is over the surface of the sphere, or R, or equal to ρ. The integral in EQ, as, can be evaluated in closed form by expanding all quantities in the integrand in terms of spherical harmonics, y, 1, in the primed coordinates, and y, in the unprimed, farbelled coordinates. First, convert the spherical vector into a sum of unit Cartesian vectors, and y in the x and y directions, equal to in plus 9 degrees Celsius. Next note that sin plus x minus 1. And synchrony, the exponential in the integral has the expansion 35, 1 to 0 r, where the asterisk denotes complex conjugation, using the orthogonality property of the spherical harmonics. Form y st equal to 6 times 6 MNM 40. A little algohen shows that, finally, I equal to xg ko 414. Where is the unit spherical vector in the far field? If the product k-re is one of the zeros of J, k-re, then the amplitude of the outgoing electric field due to the I1 surface radiation goes to 0 more quickly than the inverse of the distance in the far field. The fields at the surface of a plasmoid with this radius will therefore not radiate. An exactly analogous argument shows that the I1 magnetic surface celled will not radiate. There is an interesting interpretation to this result. It was shown in SEC 9 that it is possible to have physically realizable fields outside a plasmoid such that no discontinuities occur at the boundary. In general, if such a situation would arise, the external field would be exchanging energy with the plasmoid, even though the net exchange would be 0. At the radial that correspond to zeros of the spherical Bessel function, call them resonances, this exchange of energy is halted. It would appear that under such conditions plasmoids would be more mechanically stable. The reasoning for this is that momentum transfer and energy transfer are related. Away from resonance, the energy and momentum balances are maintained by exchanges between the inside and outside of a plasmoid. Disruption of either the flow from the inside to the outside or the outside to the inside will produce a net momentum transfer rate, which is equivalent to a net force. At resonance, forces arising from fluctuations of the fields would thereby be minimized. 41. Appendix B, a numerical example. On the basis of anecdotal evidence, very energetic plasmoids known as ball lightning may have total energy contents of 1 megajoule with a radius of 10 centimeters. With no further junification, it will be instructive to calculate a set of parameters that could produce such a force-free plasmoid in the Earth's atmosphere at sea level and at 0 degrees Celsius. For a sphere with RRE 10 centimeters from EQ8, assuming an 11 plasmoid, with a radius at the first zero of GR A 44.93, assuming and will be large enough to ignore A, then the total energy will be shared nearly equally by the electromagnetic field and the fluid kinetic energy, each having about half a megajoule, expressed as an integral, m(r) power per s510, where m(r) is defined by EQ 8, with I equal to 1. Direct integration shows that Im, R, panda equal to 3537, so that E1 equal to 3.566 ec 10 deg volts meter, taking Azure 1 and EQ 58 1.759 10 x 3.566 10 deg 0 1 times 1 equal to 7.92 Xerox 1011 is equivalent to a 126 GAZ field with K 2,642 meters to satisfy the second part of EQ 35. This value of K must be changed to, slightly, 42. K 2,686 meters, which is equivalent to a 128 GHz field. From EQ 38, the charge density is PE equal to minus 32.63 cool M3, amounting to 8.532 times 10 electrons, considering that there are about 1.12610 diatomic molecules of gas in the plasmoid, on the order of only 1 to 2 molecules in 10 needs to contribute an electron. At the surface of the sphere, from EQs 5, 20, and 27, the speed of the gas U is a function of the polar angle 9, equal to 1.431 Timostenosin meters sec, while S represents a very large speed. It is not true that the plasmoid will be travelling at 955 meters SEC, the equivalent solid sphere speed to match the surface speed. The reason is that the plasmoid was assumed to be created in a quiescent atmosphere. Analysis of the Navier-Stokes equation shows that the boundary layer emerging from the surface of the sphere as a result of the surface motion diffuses like a thermal wave. To grow out to a distance of 1 extra RE takes on the order of, at equal to pi, V equal to Boyne first, 32 x 10 equal to 757, whereas the kinematic viscosity of air at 1 atm and 0 degrees Celsius. In the first few seconds, the plasmoid will therefore hardly be moving relative to the quiescent atmosphere. On the order of tens of seconds, some motion will be evident, but it is not clear that the plasmoid has a lifetime long enough to get up to any appreciable speed. Its entire lift time, then, may be spent floating, or being carried by air currents, or responding to electrodynamic forces. It is instructive to scale the radius down to 50 micrometers. The total energy, assuming the A-K ratio stays the same, might naively be projected to 500 joules. Since the charge density will go up inversely as the square of the radius, the density of the plasmoid must be increased. Since only about 1 molecule in 10 will be ionized in the larger system, 43. A density corresponding to about 40 times sea-level atmospheric air must be assumed, which will be totally ionized. The wavelength of the trapped radiation will be equal to 1.17 pm in the infrared range. The surface speed, EQ, B8. It'll be U equal to 7.1610 force in 0, with a maximum internal speed of 2.2 x 105 meters. C, STH, not relativistic. The number of free electrons will be 4.3 times 1013. It would take on the order of 8 milliseconds for such a plasmoid to come up to speed at Oh's shell. At different temperatures, where the kinematic viscosity may be higher, this time could be much shorter. The assumption has been that the ambient atmosphere is also at a density 40 times that of sea-level air. It is not clear how the stability will be affected if the plasmoid travels into a lower density and/or pressure region. The electromagnetic pressure, balanced by the vortical field, is almost 1010 atmospheres. If even 1 joule is trapped, the pressure is on the order of 10 T atmospheres. It would seem that a perturbation of a few atmospheres of pressure may not be immediately destabilizing. More work must be done in this area. 44. Appendix C. Ad hoc field terms. In this appendix, terms will be added to Maxwell's equations that will allow true discontinuities to arise in the tangential components of electromagnetic fields at surfaces, generating accompanying surface conditions that cannot be derived from the usual set of Maxwell's equations. It should be understood that there may be no physical justification for these terms. They serve as an illustration that it is possible to assume new operators in Maxwell's equations that will not affect any solutions that are continuous, yet can give a contribution at a field discontinuity. The terms to be eventually introduced are classically unobservable, because the electromagnetic cell is classically assumed to be analytic everywhere. An objection may be raised that the introduced terms are not Lorentz invariant. In fact, they are. Lorentz invariants will be investigated separately. The important point is that classically unobservable terms can be added to Maxwell's equations, causing observable deviations from the usual formulation at true field discontinuities. Consider the operator O acting on the vector function mr at a point r. Ohm r equal to dt x tvm, r, where r is the unit radial vector centered at r, and the integration is over the full force irradians. From the properties of the gradient operator, this can be written omx equal to x. Integration in EQ, C2, is over the angular parts of the integrand. The operator 8/8 plus does not affect the angular parts of MR. In general, any wave function obeying Maxwell's equations can be expanded as a sum of multipole fields in the form 38. Mx equal to plus jam, where T, M, is a vector spherical harmony, as are complex constants, and 45, R, are functions of the radial distance from the center of the expansion. The description of a wave function using EQ, C3, is also known as a Helmholtz decomposition. Vector spherical harmonies are orthogonal on the surface of the unit sphere, that is, where the asterisk denotes complex conjugation. The unit radial vector can be expressed as T, var, COA. Similarly, the unit azimuthal vector can be written T110, A. From the rules for coupling representations of the rotation group, 25, the only terms in the multipole expansion of MR that can contribute to the integral in EQ, C2, are those associated with T1.1, 15 meters less than or equal to. When expanded about different origins, the vector function M, R, will appear to have differing amplitudes associated with the vector spherical harmonics T1. The amount of T1 at a point of expansion of MR is proportional to 5xm R at that point. The integral in EQ, C2, will generally define a different vector at each point R, depending on the local expansion of MR about the point R, if this local expansion does not have harmonic terms of the form T1, M. There will be no contribution at that point. It is now clear what form an operator can take to give no contribution when applied to analytic vector fields arising from solutions of the classical Maxwell equations. Jm, E, equal to xm, R, Tm, R. 46. Tm, R, equal to m, E in EQ, C6, is a linear operator that gives a null result when applied to an analytic multipole field. At a discontinuity in the field M, R, the radial derivative term in EQ, C2, will produce a singularity in the neighborhood of the discontinuity. It should also be noted that removing harmonica of the form T1, 1m does not affect the vector field MR at R equal to 0 because Ling equal to 0, 10, therefore 10 to 14, M, R, Tm, R equal to M, 1, or, which means that if the function M, R, has a discontinuity at R the integral in EQ, C2, will define a generating function for jumps in the field M, R. In the sense of the theory of distributions, Lisa rigorously, the integral in EQ, behaves like a delta function at discontinuities in MR, is finite at discontinuities of the gradient of MR, and is otherwise Dego. Maxwell's equations can be rewritten for any given time harmony frequency W in vacuo, incorporating the operator VXH R plus GO R equal to IDB R plus JR and P plus GRO R equal to IWO R, where the time harmony factor is XP, IWT, and the numerical factors G and GG will be determined below. The constants Gy and Gg can be determined by assuming that no current will flow on the surface, defining a discontinuity in either E or H, the usual method for deriving. 47. The current at a boundary can be modified to find Gy and Gg. Enclose a small portion of the boundary between two regions where either H or E has a jump discontinuity with a closed curve in a plane that cuts through the boundary. In the usual proof, both sides of EQ, C10, for example, are integrated over the area of the closed curve. Stokes' theorem is applied, and the current flowing through the area is found to be equal to the line integral of the component of H tangent to the closed curve. At a discontinuity, the current flowing through the closed curve is proportional to the difference in tangential components of H on both sides of the boundary of the discontinuity, I, dual H1, H2, where n is the unit normal to the boundary, pointing from the region with the field high into the region with the field H1. At a field discontinuity, the integral of OR over the surface of the closed curve, discussed above, is proportional to the right-hand side of EQ. C12, it can be shown that if no current will flow tangential to true field discontinuities, it can be argued that Maxwell's equations, including terms with EQ, C13, are Lentz invariant. The logic is as follows. All observers moving relative to an analytic C. Chromagnetic field will conclude that the field they see is also analytic, and the terms will not contribute. On the other hand, any true discontinuity in either the electric or magnetic field will be described differently by different observers, but all observers will agree that no current would be flowing tangentially to the boundary between the regions where the discontinuity occurs. The reader should again be cautioned that the added terms in Maxwell's equations may have no physical justification. Experimentally, effects such as ball lightning and anomalous charge to cluster formation occur in the vicinity of very strong local discharges that may cause field discontinuities. The purpose of this appendix is to show that such effects can arise from terms that are classically unobservable, causing no changes whatsoever in any other solutions where tray discontinuities do not arise. Applied to the force-free case, for cases that functionally look like EQ, 8, of the main text, at a radius corresponding to a zero of the function, G, R, the fields are tangential to the spherical surface. A discontinuity at this surface equivalent to a drop to zero fields outside the plasmoid with large fields inside will not need a set of boundary currents to sustain the wave functions. Indeed, the remarkable special case, called avacted in the text, wherein a spherical non-propagating field is trapped in the vacuum, becomes realizable. If the above theory applied at zero frequency to perfect superconductors, where the transition from non-zero field to zero field, outside to inside, occurred as a true discontinuity, there would be no current residing on the surface. Since the quantity fix H appears in the equations for the external field, not the current, per se, A, there would be no obvious contradiction introduced into classical electromagnetism. The logical extension of such assumptions would be the existence of zero-frequency vactoids, having a static electric or magnetic field trapped in, say, a toroidal closed loop with no enclosing currents. Any further speculation concerning such pathological states of the electromagnetic field is beyond the scope of this report. At the present state of development of technology, it is impossible to either accept such extra terms or reject them out of hand. 49. Appendix D equation 23 expressed the energy in the electromagnetic field of a plasmoid as having a time dependence. Since energy must classically be conserved instantaneously, the time variations must be accounted for by the kinetic energy of the electrons oscillating along electric field lines. When this energy is added to Q in EQ 23, the time dependence of the total energy of the plasmoid at any point should be independent of time. This is easily proven. The kinetic energy of an individual electron at the point R is Kp, where m is the mass of the electron and v is its non-relativistic velocity. The kinetic energy of the electron gas can be written in terms of the current density at R. 7. T VDU, where 1.622 Rs 1019 C, using EQ 37, and the time dependence of the current, T equal to 100,863, Wt plus 9, J, or ER do. Since the spatial part of the vector potential can be related to spatial part of the electric celled. AR equal to ER then. T equal to cos 3, Ut plus 4, AR minus 3, RD's 50. The quantity Q plus T greater than 0, which is the total energy of the plasmoid, is now independent of time. Although the total energy is positive, two parts of the sum, that is the second integral term in EQ, 23, and the electron kinetic energy, are equal and opposite in sign. Even the local energy densities associated with these terms are equal and opposite in sign, the kinetic energy density always being positive. Only frequencies above the critical frequency will be considered, since electrons then carry the current. The free electrons making up the current can be considered as moving about the minimum of a potential well whose average depth at any point, r, is 1/4 A, 5r, J, 5r. From EQ 25. The depth of this equivalent potential well increases quadratically as the frequency increases. The argument made in the main text is that if the electronic kinetic energy is not changed, a small local geometric perturbation will raise the energy of the plasmid. That argument was based on the out-of-phase relationship of J, R, and A, R. Another simple argument can be made that geometrically perturbing the plasmoid raises its energy. Following Gecker, 21, p80. Each oscillating electron can be thought of as an oscillating electric dipole, whose potential energy is at a minimum when its dipole moment is aligned with the fields. If the perturbation does not leave the plasmoid in another force-free state, a torque is needed to turn any given dipole to a different orientation. This torque will have components arising from the electric as well as from the magnetic field. A restoring torque will tend to line up the dipole moment with the electric field and force the electronic motion to follow magnetic field lines. Since both the electric and magnetic fields are parallel, all the contributions to the restoring torque in a small perturbation will add constructively and be opposed to the perturbing motion. 51. Appendix E52. Non-radiating harmonic fields that can confine plasma currents and charges. Jack Nachamkin, University of Dayton Research Institute, Phillips Laboratory, OLAC, PL, RKF Edwards, AFB, CA 93,000, 523 to 5,000. Abstract. Elementary theory of force-free fields is applied to electromagnet Cali excited charge densities. It is shown that mechanically stable non-radiating modes may be excited in plasmas by harmonic fields, even in the absence of DC magnetic fields. The free charge den Eiley needed to sustain a stable spherical non-radiating mode can be shown to be uniform and dependent only on the electromagnetic Wava number and spatial extent of the mode in a neutral plasma. The time-averaged electric and magnetic fields in such modes are all zero. A virial theorem check verifies the consistency of an intuitive approach and a more rigorous Lagrangian formulation. Electromagnetic stress effects, which can be accurately balanced by vortical fluid motion, are ignored. L introduction. If the vector field HR is a force-free field, then Vxh equal to Gh, where A is a complex constant, it may seem strange to imagine a vector field that is proportional to its own curl, without the field being identically null. Nonetheless, such fields can be constructed, at least mathematically, having non-zero magnitudes. The properties of such fields may be very valuable in diverse areas of engineering. For example, if the windings of a DC electromagnet followed the streamlines of a force-free celled, the force on the wires, due to the magnetic field they produced, would be zero. Hence the name for the fields. In fluid dynamics, the contribution of the Vx-Vxv term in the Navier-Stokes equation is zero in a vortical fluid mode, whose flow follows streamlines of a force-free field. Such modes are known as Beltrami vortices in fluid dynamics. 1. In electromagnetic engineering, electromagnetic excitations that obey EQ, L, can be shown to exist in vacuo, as well as in the presence of charge and currents. These modes are stationary, that is, provided with the proper boundary conditions, they will not propagate. In this note, some of the simple properties of force-free non-radiating fields will be derived. Any references to a non-radiating mode in this note will always imply reference to a force-free non-radiating mode. Applications will be made to the theory of stable electromagnetically self-confining excitations that may have long lifetimes and very high free charge and energy densities. Many of the phenomena to be described may never have been observed. Some of the results of the simple theory may explain experiments performed by Bostic and his associates, as well as results reported by Puthoff and Shoulders. 2. The idea of applying the force-free mode to confining plasma is not new. 3. 4. Techniques employing names such as the spheromac and compact toroid, which nominally depend on force-free plasma motion, have been implemented with varying degrees of success, m. In these schemes, the object is to induce the gross fluid velocity of the plasma to conform to a Beltrami vortical mode. This lowers the magnetic interaction energy and presumably raises confinement times. A common feature of the past applications of force-free modes to plasmas is that the fluid, or ion, velocity is non-zero and directed along the ergodic streamlines of a Beltrami vortex. The stationary, zero-frequency, magnetic field also lies along these streamlines. Since the plasma is assumed to be neutrally charged, Maxwell's equations predict that the zero-frequency magnetic field is not necessarily accompanied by an electric field. In what follows, the force-free idea is taken one step farther with the introduction of a high-frequency electromagnetic field. A self-consistent solution will be shown to exist that allows the electric and magnetic fields, as well as the current, to have the force-free form. Beyond a critical frequency, the magnetic interaction energy of the oscillating free electron density is not only minimized, it changes sign and becomes negative. An initial physical model is postulated that has the ion stationary, that is, there is no net fluid motion. Only the free electrons oscillate very nearly along force-free streamlines. Applying Lagrange's equations to this model forces the free electron density to have a specific value with respect to the size parameter A and the frequency, but independent of the amplitudes of the fields. It will turn out that if A is a constant uniform free charge and ion densities are consistent with force-free high-frequency electromagnetic fluid modes. This model is incomplete, owing to the fact that the free electron gas, with non-zero mass electrons, cannot exactly oscillate along curved electric field lines, and will thereby experience electromagnetic stresses. These stresses are, at high frequencies, equivalent to a positive pressure field proportional to the square of the electric field, 20, a direct, 2. Application of Bernoulli's theorem, 2, says that introducing a fluid velocity whose square is proportional to the square of the electric field, that is a Beltrami vortex, will counterbalance the major electromagnetic stresses. The introduction of fluid vortical motion for enhanced stability will not be addressed in this note, but will not affect the results derived here. The virial theorem predicts that no excitation can be confined indefinitely by only classical electromagnetic fields, even in the relativistic limit, 10. The model proposed here does not violate this prediction. Application of the virial theorem, ignoring radiation from surface currents and non-linear effects, yields conditions for long-term stability that are identical to those derived for self-consistent force-free motion of non-zero mass electrons in an electromagnetic field. The major approximation made is that the massive electrons exactly follow the curved force-free electric field lines. In a sequel, this approximation and an analysis of the virial will be pursued. It will be shown that there may be trade-offs between energy density, frequency and confinement time for a fixed-sized excitation. Second, kinematics of the fields. Taking the curl of EQ1, VX Vo VH V3H, and realizing that, since H is derived from a curl, fifth equal to 0, then it follows that H obeys the vector Helmholtz equation. V3H plus a 3H equal to 0. Equation 4 is the key to searching for solutions to EQ. 1. Not all solutions of EQ. 4 will be solutions of EQ. 1. But all solutions of EQ. 1 will be solutions of EQ. 4. The process of generating solutions to EQ1 can be approached in several ways. One way is to choose any vector field that obeys EQ4 and successively take its curl, noting all new terms that arise. If the number of independent terms stops increasing, form a linear combination of the final set of terms such that the linear combination obeys EQ4, starting from 3F1 equal to sin GAR. The resultant force-free vector field is fin R04 equal to 1 plus 1 cosine R plus 1 R A sin GR sin. Whereas any integer, I greater than 0, G is the familiar spherical Bessel function, and the vectors plus 6, and are the familiar right handed 3D polar coordinate unit vectors. The vortical field described by EQ 6 has a useful application, as will be shown below. It is somewhat tedious but straightforward to show that 5xf1 a r6 6 equal to Arphia r section 6. A somewhat more elegant expression for force-free fields can be derived from the properties of the rotation group. Using the notation in Rose's book 12 for the vector spherical harmonics T, L, M, force-free fields can be immediately written that correspond to the 21 plus 1 dimensional representations of the three-dimensional rotation group. BLM equal to GR plus I plus EG 1 AR 2 minus 1 M VG plus 1 AR 2 plus 1 M, where B, M, is a force-free field for 1 greater than 0 and 15th MSL. It is not clear at this time that the bin form a complete set for the expansion of general force-free fields. Note that the spherical Bessel functions can be replaced by spherical Hankel functions and that A does not have to be real. Note also that force-free fields can be expanded in cylindrical A coordinates and may be synthesized using functions obeying the scalar Helmholtz equation, yet possessing singularities appropriate to conical geometries. Neither of these latter solution sets will be pursued in this note. For constant values of A, Zaghloul and Barajas employ Hanson's straightforward method to synthesize force-free vector fields from arbitrary solutions of the Helmholtz equation. The reader is referred to their paper and Stratton's book for details. 131,415. The real fields, Phi A, from EQ 6, can be shown to be a subset of the set of fields bromine, from EQ 8. The explicit forms displayed in EQ 6 for the field components, however, are easier to deal with analytically. Consider a vortical velocity field with the form FIIs. Within a common constant factor imparting the correct dimensionality, the time rates of change of the coordinates are 1 plus 1, consin minus 1, or 1 to 1, A, 0, and R in, starting with EQs. 9, 11. It is possible to integrate the trajectory of a point having the above components of velocity. The time, t, can be eliminated from any pair of the expressions. If EQ 10 is divided by EQ 9, the resultant equation, tan of G, R, can be integrated analytically to obtain sin equal to a RG R, where A is a constant. Equation 13, coupled with the non-analytic equation for 4, 1 plus 1, determine streamlines, a very important property of EQs. 9, 11, is that for at every value of R, for which G, arm, equal to 0, the radial, P, and azimuthal, 4, components of the vector fields FLB vanish. At any such R equal to the only component of the field is the longitudinal component. Vortical fields like phi have, then, a layered structure. It follows that if the simplified longitudinal boundary condition at any of the Rm can be met everywhere on the surface of a sphere, then the field internal to the sphere will obey EQs. 9, 11. At all times if they obeyed these equations, and EQ 1 for R senior, or if force-free fields represented stable configurations for the physical system under consideration. For the special case 11, the longitudinal boundary condition is met by the velocity components of an incompressible inviscid fluid at the surface of a sphere immersed in an infinite uniform flow, or the magnetic field at the surface of a spherical superconductor in an otherwise constant field, or, in short, by any harmonic field whose radial component is 0 at the surface of the sphere R. The I, one case would be indistinguishable from a solid sphere, with no internal structure from the outside. In the next sections, arguments will be made to show that a conducting plasma may be excited to sustain a non-radiating electromagnetic mode whose electric and magnetic selds obey the force-free conditions. Arguments will also be made to show that these modes can be stable and self-confining when terminated with the appropriate boundary conditions. The current in the plasms will be forced to flow along the streamlines of a force-free vortex. Electromagnetic volume stresses will be ignored in this note, but are not negligible. These stresses can be counteracted by fluid motion. A full discussion of the interaction of fluid stresses and electromagnetic stresses will not be needed to understand the principles presented here. In the final section, and in the appendix, some speculations will be made as to how this theory can be applied to predict the existence and properties of stable particles that are described by non-radiating modes trapped in spheres of neutral plasma. Third, interaction with electromagnetic fields. Let H in EQ1 be a magnetic field. If E is the accompanying electric field and J is the current, in otherwise free space Marwell's equations are Vxh4 plus J and O Vx equal to Po, where EO and Po are the permittivity and permeability of the vacuum. Assuming a time harmonic dependence, EQs 1, 15 and 16 imply that E equal to OAH, vol, where 0 is a scalar potential. The vector potential A is then A equal to low, Rom the Lorentz condition, fifth plus EU equal to 0. It follows that sequel to 0 equal to, because VH equal to 0. The above choice for the vector potential was not unique. It was made to force the current to also have the form of a force-free field. To see this, solve for J, A, 1, G, where K is the free space wave number W2, from EQ 21. It follows that fifth J equal to 0, and that J is also a force-free mode if H is a force-free mode. This implies also that at any frequency greater than 0, a force-free field current does not produce a scalar potential. Therefore, an excess of charge of a single sig entrained in a force-free mode in a time-harmonic electromagnetic field will have a non-time harmonic electrostatic field associated with it. In other words, the charge density in a stationary non-radiating mode may not be uniform in space, but it is not a function of time. It will be shown below that the charge density must also be spatially uniform. 7. Note that if K equal to I, with real A, the current becomes 0, and the non-radiating mode corresponds to a vacuum excitation of the electromagnetic field having finite energy density and 0 mean momentum density. Momentum density is proportional to EXH, whose mean is 0 here. Note also that the relative phase of the current and the magnetic field it generates reverses at K equal to Ji. As the frequency W increases, the value of K and subsequently the absolute Vaut of J compared to H increases beyond the frequency when K equal to Ji. Equation 21 has some interesting consequences when the interaction energy of the current and the magnetic field is considered. Following the logic in Stratton's book 13, but accounting for time harmonic variations of the field, an expression can be written for the RMS energy, Z, of the current, J, in the presence of the vector potential, A, the asterisk, means complex conjugation. G-qual, from EQs 18 and 21, this becomes low 1IH12 edu. For real values of the magnetic interaction part of the energy density becomes negative at high frequencies. WCO, C is the speed of light. The implication is that force-free mode currents created in short wavelength electromagnetic fields residing in local minimum of potential energy, BRI mechanically stabilized by the electromagnetic fields. From EQ 22, the higher the frequency of the field, the more bound the current. In order for the above analysis to apply, assuming its interpretation I are correct, it has to be possible for the field to couple to the current and the boundary conditions have to be met. In a way, the stream lines of a force-free Dor vortex seem to act like waveguides, allowing modes to penetrate if they are small enough to fit. At the critical frequency, we equal to CO, an electromagnetic free space mode can exactly match the size of the force-free mode. At higher frequencies, free space modes can fit inside the force-free mode and stabilize it. Fourth, energy, force, and momentum considerations. The ultimate practical question is, can this theory be applied to produce stably confined plasma, and if so, how? First, consider the forces on individual blobs of charge that make up a current. The Lorentz force on a charge density, P, moving at a velocity v in an electromagnetic field is 8. F equal to P, E plus Bovchi. Since J equal to PV, this reads F equal to PE plus mod XH equal to PE for force-free modes. In other words, the only non-zero time averaged force acting on the charge in an isolated force-free mode arises from the zero frequency electrostatic field delay to the other charges. In a neutral plasma, the electrostatic forces are evidently zero. IR excess charge is present in the current. An electrostatic field will perturb the trajectories. It will be very instructive to electromine the sum of the magnetic interaction energy and the kinetic energy to determine T plus stability of the overall system. The reason for ignoring the energy in the Ostuaturg electric field is that it does not directly contribute to the stability of the current. AI infinitesimal change in current will affect Ti-magnetic interaction energy and the kinetic energy only. The electric field will, however, determine the kinetic energy of the equilibrium system. At high frequencies, the motion of the charges, ignoring electrostatic and outside mechanical forces, is small displacement oscillation about an equilibrium at the frequency of the field. It is important to realize that there is no net motion of the charges. The background neutralizing ions are also assumed to be motionless. The motion of the charges, assumed to be carried by electrons, is driven by the electric field, which is parallel to the current. Calculations will all be non-relativistic. In a simple-minded initial intuitive approach, which admittedly should not be giving the correct results, Newton's law F equal to ma will be applied. The volume force on a charge distribution with density P is Pe. The acceleration is the time derivative of current divided by the charge density, P. Pe equal to Pm, P, where Pm is the mass density of the charge, from EQs 17, 20, and 21, putting all quantities in terms of E and rearranging P, 8, 2. Cancelling the IW, and assuming that all the current will be carried by electrons, the expression for the electron cloud charge density is 9. 7 Ka, 28, where m, E equal to 5.09 x 10 to 12 kg. Cool is the mass-to-charge ratio of the electron. An important note is that EQ, 28, is only valid for Ka. The reason for this is that the sign of the charge density distribution changes at Ka, and for Ka the sign is inconsistent with negative charge carriers. This is an important factor in stability considerations. 11. Substituting for quantities to obtain the R kinetic energy density equal to 1. Newton's law, in its simple-minded form applied above, is not strictly valid in this case. A constant charge and mass density was implicitly assumed from the outset if Newton's law is applied. The fact that a spatially uniform charge density results shows that the assumption leads to self-consistent results. In the appendix, the Lagrangian formulation of the system will be investigated. It will be shown that the result in EQ, 28, can be derived without assuming uniform charge density. It is valid under all conditions where overall charge neutrality is maintained and gas dynamic effects are ignored. Equations 28 and 29 are extremely important from a practical point of view. From EQ 28, it is evident that the amount of charge participating in the motion is determined only by A and the frequency. Furthermore, as proved in the appendix, uniform volume charge density is a mandated, variationally correct solution of the Lagrangian equations. An interesting point is that the free charge density is independent of the amplitude of any electromagnetic field quantity. By assuming that an Ohm's law can be written in the form J equal to W for a non-radiating mode, then the conductivity W is purely imaginary and can be written WLRT. So that at high frequencies a non-radiating mode becomes purely capacitive with an asymptotic specific capacitance equal to 85 pfm. The endeavor to drive modes at higher and higher frequencies might encounter a difficulty equivalent to trying to match a very small impedance. Very high field strengths might be required in small, order of 10 wavelengths on a side, volumes. Laser radiation may be a practical solution as a high-power driver. 10. From EQs 23 and 29, the sum of the kinetic and potential energies relevant to stability of the overall motion is 0 if surface stabilizing currents and vortical fluid motion are neglected. Note, however, that the total energy of the system is positive. As the frequency increases beyond the critical frequency, the amount of charge contributing to the current increases, the kinetic energy increases, and the potential energy decreases for constant absolute value field strengths. Beyond the critical wave number, the kinetic energy increases asymptotically like the square of the frequency. For energy and momentum balance, a critical amount of free charge must be available. If not enough, or too much charge is present, the conditions of the motion may not be met at the given frequency. In addition, the system cannot radiate from its interior because the E and H vectors are parallel everywhere internally. Evidently, there is no restriction on the amplitude of the electromagnetic fields within the mode. Since the theory has been derived here for non-relativistic plasmas, there may be some eventual dependence on field amplitudes in ultra-energetic modes. For very small field amplitudes, fluid and thermal forces might disrupt a non-radiating mode. When real systems are considered, massive electrons, which carry the current, cannot constrain their motion to the curved electric field lines. This introduces a constraint on the field amplitudes, such that the excursions of the electron positions from the field lines must be small. Field curvature leads to electromagnetic stresses that induce electronic drift across field lines. The interaction of the resultant pressure tensor on the free electron gas with the overall fluid is very important. None of these complications, however, will Pursued bear. The consequences of this approximation will be discussed in a sequel, 11. In what follows, it is assumed that a finite spherical region of a short wavelength non-radiating mode is sustained by matching only the electromagnetic boundary conditions at a fixed radius. As was mentioned above, modes can be chosen such that the boundary conditions reduce to only tangential conditions on the velocities and the fields. This can translate into a requirement for surface currents to produce jumps in the electric and magnetic fields, going from the force-free fields inside the spherical region to the free space fields outside, and/or vortical fluid motion that can counteract the electromagnetic surface and internal stresses. No mechanism will be described to fully invoke the needed conditions. They may be very difficult to reproduce physically. If such boundary conditions were not provided, however, the non-radiating mode would decay. The speed of this decay has not been calculated, but it seems intuitively reasonable that systems with large densities of kinetic energy would take longer to decay than those with small densities, if fluid dynamic effects are ignored. Surface currents and vortical motion serve the purpose of counteracting the 11. Normal electromagnetic stresses, which would otherwise tend to force the excitation to expand. 0 total energy of the free electron cloud above the critical frequency means that the electronic motion is in neutral stability, but might show some rigidity in response to compressive forces. Unless other mechanical forces, such as internal vortical motion, are involved, a non-neutral, classical force-free system will self-destruct due to internal electrostatic forces. An ionized fluid or neutral plasma will barely be stable if mechanisms are not present that can lower the overall energy. Surface currents contribute to stability by a pinch mechanism, which will effectively be a surface tension. It must be emphasized that lowered, energy due to either the pinch effect of currents or vortical motion are absolutely required for stability. What makes the present model attractive is the minimization of the body forces induced by the interaction of the current with the force-free electromagnetic celled. By themselves, these body forces could tend to severely limit the lifetime of an excitation. The question of meeting the boundary conditions for the electromagnetic field also has to be addressed carefully. A non-radiating mode with a given harmonic internal current will generate external harmonic electric and magnetic fields that do not have the force-free form. It is a simple matter to say that the correct boundary conditions on the field, that is, those that do not permit radiation to escape from a truncated volume, can be reproduced with surface densities of electric and magnetic current. There are difficulties with such a solution. The first difficulty is that a surface density of magnetic current may not be achievable. Such a current may be approximated, however, by eddies at the surface. The pure electric current boundary condition, on the other hand, can be met by having a physically achievable surface current distribution. In either case, large accumulations of surface charge would be required to produce boundary currents. The stabilizing effects of such currents can also be achieved by setting the supporting fluid into a vortical flow, counteracting the electromagnetic stresses. This point will be discussed further in a sequel, where it will be shown that the proper choice of an excitation radius for a given frequency can drastically affect the radiation boundary conditions and stability. Another way of looking at the overall picture is to realize that in a harmonic field, the electric field can have a minimum. The first derivatives of the potentials can all be zero, and their second derivatives can all be positive. Unlike the physical situation giving rise to Earnshaw's theorem, the components of the potentials and fields obey the Helmholtz equation instead of the Laplace equation. This allows the possibility of stabilization of charges and currents under the influence of only self-consistent harmonic electromagnetic fields and perhaps added vortical fluid motion. In short, boundary conditions for truncated force-free modes that are met by surface. 12. Currents and/or internal fluid motion may lead to plasma excitations that are mechanically stable and relatively long-lived. Puthoff has suggested that by introducing the zero-point field, ZPF, stability may be greatly enhanced. Conducting systems will experience a net outside pressure, analogous to the Casimir force, due to the exclusion of ZPF modes. The more conducting, at higher frequencies, the more ZPF modes will be excluded from the interior, and the higher the pressure differential. Additionally, the energy to stabilize non-radiating modes might be available from the higher frequencies in the ZPF once the mode has been formed. If the above theory is to be believed, the ZPF may play an important role in stabilizing non-radiating modes. Detailed calculations would have to be done to determine critical densities of charge versus size and frequency for all the quantities to come together exactly right. Further research would investigate how to inject charge into already formed modes and have them stabilized by higher frequencies that come from directed sources or are present in the ZPF. A final point relates to the initial construction of non-radiating modes. If these modes are stable, why are they not a common phenomenon? Actually, they might be quite common in nature, but with short lifetimes and low energies. They also might be very small and hard to detect. Considering that the most logical place to look for charged, high-frequency, non-radiating modes would be in powerful electrical discharges, such as found in lightning strokes, the surrounding phenomena might mask their occurrence. In the laboratory, strong microwave or laser, perhaps accompanied with DC, discharges with possible extra electron injection might be conducive to non-radiative mode production. Discharges in a highly ionizable gas, such as cesium or Penning mixtures, under the above conditions may enhance the effect. In any case, detailed calculations and experiments might have to be done to determine optimal conditions such as discharge field strengths, gas density, frequency, electrode size, etc. The investigation of non-radiative mode effects may be very fruitful in the future. For example, rigid, non-radiative composite particles containing large numbers of fusible ions may be compressible in strong quadrupole fields without undergoing chaotic turbulence-like instabilities and have lifetimes consistent with producing copious thermonuclear reactions. Large diameter modes, with significant lifetimes, might be capable of storing large amounts of energy, etc. The field seems to be wide open, hinging on simple experiments that may prove the basic principles. 13. References. 1. Truesdell C. The Kinematics of Vorticity, Indiana University Press, Bloomington, Indiana, 1954. 2. Bostic Wabu and others, Second International Conference on Energy Storage Compression and Switching, Venice, Italy. New York, Plenum Press, 1983. H. Puthoff, Jupiter Technologies, Personal Communication, 1990. 3. Taylor, J.B. Realization of Toroidal Plasma and Generation of Reverse Magnetic Fields, Phys. Reverend Lett. 33, 1139, 1974, 4. Taylor, J.B., Realization and magnetic reconnection in plasmas, Reverend Mod, Phys. 58741, 1986. 5. Firth H.P. The Compact Torus Concept and the Spheronac, Proceedings of the U.S.-Japan Joint Symposium on Compact Toruses and Energetic Particle Injection, PPL, pp. 3-7, 1979.
6.
Rosenbluth, M.N., and Emin-Bussock, M.H.D. Stability of Spheromac, Nuclear Fusion 19, 489-1979. 7. Schmidt G. Virial Theorem for Plasmas Phys. Fluids, 3 481 1960. 8. Rosenbluth, M&M, and G.W. Stewart, Relativistic Virial Theorem, Phys. Fluids, 6 452 1963. 9. Gurdjieff, E. and R.C. Stabler, Self-Confinement of Plasmas, Phys. Fluids, 7 920 1964. 10. Liboff R.L. and T.J. Lai, Plasma Virial and Equations of State for a Plasma, Phys. Fluids, 11 1943, 1968, 11. Nachamkin J. Vortical Stabilization of Non-Propagating Electromagnetic Bacitations in Plasma. Manuscript, to be submitted for publication. 12. Rose Me. Elementary Theory of Angular Momentum New York, J. Wiley Sons, 1957, 13. Stratton Essay, Electromagnetic Theory New York, M.C. Graw-Hill, 1941. 14. Hansen W.W., A News 2 P.E. of Expansion in Radiation Problems Phys. Reverend 47, 139-143, 1935. 14. 15. Zaghloul H. and 0. Barrages, Force 50 Magnetic Feeds, Am. J. Phys. 58, 783-788, 1990. 16. Harrington R.F., Time-Harmonic Electromagnetic Fields New York, M.C. Graw-Hill, 1961, 17. Puthoff He, Condensed Charge Technology and its Potential Impact on the Electronics Industry Meeting of the Society for Scientific Exploration, Palo Alto, June, 1990. Boyer, The EAT, The Classical Vacuum, Scientific American, August, 1985. Goldstein H., Classical Mechanics Reading, Massachusetts, Addison Wesley, 1959, 19. Erickson M., C. S. Ward, S. C. Brown, and S. J. Buchsbaum, Containment of Plasmas by High-Frequency Electric Fields, J. Apple, Phys. 33, to 2429 to 2434, 1962. Gecker L.R. Interaction of Strong Electromagnetic Fields with Plasmas, Oxford, Clarendon Press, 1982, 21. Bachelor G.K. An Introduction to Fluid Dynamics, Cambridge, Billiversity Press, 1967. 15. Appendix. The assumption that a self-consistent charge distribution, neutralized by charges of the opposite polarity, can carry harmonic current in a non-radiating mode leads to equations for the charge density at any point. The Lagrangian equations for the system lead to a non-linear first-order vector partial differential equation for the charge density. It will be shown that an exact solution exists wherein the charge density is certainly uniform. Equat. 29. Will be found to be valid at all field strengths. It will also be shown that the occurrence of such modes is consistent with a uniform mass density and rigid motion in a plasma, or GAA, whose polarizability is a function of only the gas density. The RMA Lagrangian density, 18, for a current of massive particles in the presence of a non-radiating harmonic electromagnetic field in a neutral plasma, is proportional to where AM is the mass density of the current, R is the current cell's spatial coordinates, the dot means velocities, PE is the charge density, and the scalar electromagnetic potential from EQ 20 is 0. Using the relation J equal to P with equations 1, 16, 18, and 20, the Lagrangian equations for the motion can be written in the vector form, after a little algebra. 7 plus 7, 2, U, E equal to 0, 42, where M. Equation, cool, is the electron mass to charge ratio. Equation, A2, immediately yields one solution by inspection, P equal to 0, and 7, 1, plus 0, which can be solved for the same P, given by EQ 28, 16, or greater than alpha Ka. It is not clear that EQA, a 3, represent a unique exact solution for K3 a 2. The Lagrangian equations may be integrable for non-uniform density distributions. Such a case might arise for a shape perturbed away from spherical. Under that assumption, it would also be expected that an entire mode might oscillate about an equilibrium with a frequency that might be much lower than the frequency of the electromagnetic excitation. This possibility was not taken into account in setting up EQ, a 2, where it was assumed that the partial time derivatives of the mass and/or charge densities are 0. The total time derivatives of these quantities that appear in the Lagrangian equations arise only from the term plus 5p. It can now be shown that the above analysis is consistent with a null virial. The analysis below will be expanded somewhat in a subsequent note. 11. The particles in a high-frequency non-radiating plasma mode will all be assumed to perform small amplitude oscillations about equilibris, so that at any time the position S, R, T of any particle can be described by R, T, where J, RE is the time-dependent current at the space-fixed point R. The force, FRT, acting on the particle comes from the electric field. FRT equal to E. The virial theorem 18 requires that R, P, R, dV, PM. By straightforward algebra, it is evident that T, RT, R, T, dV equal to 3 R, E. RTV equal to number 17, and where the integrations are over the volume of the mode. For purely spherical modes, the natural volume for integration might be from the origin to the first zero of the appropriate Bessel function associated with the mode. Substitution of EQ, A8, and a 9 into a 7 gives JR 410, cancelling the integral from both sides of EQ, a 10, and solving for P obtains 411, which is identical to the result assumed from a Lagrangian formulation, as well as the simple analysis based on simple mechanics preceding EQ, 28. Note that EQ, A11, needs the relationship between the mass density of the electrons and the charge density, i.e. PM, PME, 5, 6, 10, 13 kg, cool, where the minus sign arises because the charge density, PA, is negative. The somewhat interesting insight from EQ, A11, is that unless the frequency is high enough, A, the required charge density for the electrons, must be positive, clearly an inconsistency. Not only must the frequency be high enough to predict a consistent charge density for the current carriers, the Mach-heavier ions are never considered capable of carrying the high-frequency current. A full virial analysis, 11, shows that one of the conditions for stability is that A2. The question can also arise as to what the allowable gas density can be in a non-radiating mode. Without taking compressible fluid dynamics and its interaction with the electromagnetic stresses into account, the density cannot be fully analysed. Further work, to be reported on in more detail at a later time, seems to indicate that when vortical motion is introduced, a stable excitation can arise that has uniform density and entropy, with a gas pressure exactly equal to the gas pressure of the surrounding atmosphere at the time of its creation, and is stable against small perturbations of internal velocity. 1. 18. In summary, the assumption that non-radiating modes can exist in a neutral plasma leads to the conclusion that the free charge density entrained by the current can be a constant throughout the mode and dependent on the free space electromagnetic wave number for a given modal A. It is also consistent with assuming that the only forces acting in the volume arise from fluid motions and the time-varying electromagnetic field in a neutral plasma. 19. Appendix F3. Virial analysis of harmonic force-free excitations. Jack Nachamkin, University of Dayton Research Institute, Phillips Laboratory OLAC, PL, RKF Edwards AFB, CA 93,523 to 5,000. Abstract. Conditions for a mole virial for electrons forming the current in force-free harmonic mode are investigated. Above a critical frequency, this current lies in a potential well whose relative depth increases as the frequency increases. Conditions for greatest stability, ignoring electromagnetic stresses, are investigated. Fluid dynamic effects are also ignored. Under appropriate approximations, the conditions for a Mole electron virial TUM out to be identical to conditions for the motion of electrons oscillating along the electric field lines in the force-free electromagnetic field, above the critical frequency. The free electron density must be uniform and depends only on the size of an excitation and the frequency of the time-harmonic electromagnetic field. Assuming reasonable limits on physical parameters leads to upper bounds on the energy content of excitations in the megajoule range for a sphere with a 10 cm radius. A negative potential well for electrons, above the critical frequency, allows the possibility of quantum effects, which are not investigated. Further areas of research are briefly discussed. First, introduction. If the vector field HR is a Beltrami, or force-free field, 13 then, VXHO, where A can be a complex constant, let H in EQ, 1, be a magnetic field. If E is the accompanying electric belt and J is the current, in otherwise free space Maxwell's equations are BVXH equal to plus J, and AN, where and J are the permittivity and permeability of the vacuum. Assuming a time harmonic dependence for all quantities, EQs 1, 2, and 3 imply that E equal to HVA, where is a scalar potential? The vector potential A is then equal to AMB from the Lorentz condition. It follows that 0, because VH equal to 0. The above choice for the vector potential was not unique. It was made to force the current to also have the form of a force-free field. To see this, solve for J equal to A1H, where K is the free space wave number, WAR. From EQ 1, it follows that Vj equal to 0 and that J is also a force-free mode, if H is a force-free mode. From EQs 4 and 8, E can also be written in terms of J, 2, E equal to WLRD. It is important to note that EQs 1 to 0 will not all necessarily bold if A has any spatial variation. It also can be shown that, starting with a force-free harmonic current that fills all of space, the electric and magnetic fields will be harmonic and also have the force-free form if A is constant. A feature of the above equations is that, unlike in a vacuum plane wave, as the frequency increases, the field energy becomes more concentrated in the electric field. For K, the direct contribution of the magnetic field energy to the total energy becomes negligible compared to the contribution from the electric cell. Indeed, for Ka, with critical frequency where it AC, the interaction energy of the current and the magnetic field is negative. In other words, the current finds itself in a potential well whose relative depth increases with frequency, all other things being equal, after the point where K equal to A. This energy well is intriguing, considering the quantum mechanical possibilities and stationary states that may arise. It was already shown that, classically, the sum of the magnetic interaction energy of the free electrons and their kinetic energy is RO. Although quantum and relativized effects may alter the picture somewhat, they will not be considered here. The above equations represent a valid solution of Maxwell's equations that can fill all of space with massless current. A more realistic physical situation realizing finite-size excitations and non-zero-mass current carriers electrons will now be considered. Toward that end, it will be shown, using the virial, that the stability of finite-size harmonic excitations in a neutral fluid be optimized by adjusting the free charge density. The optimum free charge density will be shown to depend on the electromagnetic wave number, 1, the size parameter of the excitation, A, and the condition Ka. A number of assumptions will be involved in the course of performing the analysis. The first assumption is that the background ions do not participate in the motion of the excitations, nor are they affected by any of the high-frequency fields. It is next assumed that all the temperatures are low, and the geodynamic pressures inside and outside the excitations are equal, so that thermodynamic and fluid dynamic effects will be ignored. In other words, to first approximation, the excitations to be studied will float in an ambient fluid with no net motion. The gas density and free electron density will also be assumed uniform in space within the excitation. A major result of this note will be sheer termination of the optimal uniform free charge density. The next assumption involves an approximation. It will be assumed that the electrons, carrying all the current, oscillate harmonically along curved electric field lines. This approximation would be exact if the electrons had no mass or if the amplitudes of oscillation were truly infinitesimal and the temperature was low enough. As the frequency increases and the field amplitudes decrease, this approximation becomes more accurate. Excursion of electronic motion from the curved electric field lines forces the current to 3. Have non-force-free components and can thereby lead to losses via synchrotron radiation, so it is important that these excursions be minimized. In addition, internal pressure gradients can arise if the field lines are curved. These pressure gradients, proportional to the square of the celled intensities, may become so large as to dominate any stability analysis. Nevertheless, such effects will be ignored in this note. At the outer surface of the excitation, it will be assumed that the jumps in the electric and magnetic harmonic gelds from large values inside to zero outside sustain equivalent surface currents. 3. Since these harmonic surface currents may be very large, to accommodate their size in a thin layer without large excursions of the electrons might require very large concentrations of neutralized, free charge near the surface, and therefore large concentrations of mass at the surface. These will be assumed to exist. Surface currents are invoked to prevent radiation losses. Subsequent work will deal with surface radiation in a more realistic manner. To do so here would not be appropriate. Conditions under which all the above assumptions can be met in a reproducible experimental situation will not be handled in this note, but none of the assumptions appear to violate any physical laws or introduce contradictions. Subsequent work is being directed toward eliminating the need for surface currents and using vortical fluid modes to counter electromagnetic stresses. Second, virial considerations. Consider the mean square moment of inertia, I, of the electrons in a finite volume excitation and its time derivatives, I par RdV, and, where Pm is the spatially uniform mass density of the electrons, R is the complex position vector associated with an infinitesimal blob of electrons, and the integration is over the volume of the excitation. Strictly speaking, the integrations in EQs, 10 and 11, should be summa of individual electrons, but their densities are assumed high enough for the integral to be an appropriate approximation. The quantity I's will be called the virial of the electronic motion, 44. The exclusion of the electromagnetic field from the above integrals will be discussed below. The quantity R equal to R334T is the instantaneous position of an infinitesimal volume, whose mean position is at the fixed point ρ, y, z, t, and oscillates with the same frequency as the applied harmonic field. By definition, the velocity, v, is proportional to j, z equal to j and p, where p is the spatially uniform charge density of free electrons. The charge density, Pe, is simply related to the mass density, Ps by Pe equal to E m Pm, where E m equal to 1,759 times 1011 cool. Since all the quantities are assumed to be harmonic, so that 1 equal to 3, E, then R can be written. A sufficient condition for self-confinement is that the time-integrated average of I is 0. This condition implies that the moment of inertia of the electron cloud can assume its original value any number of times and cannot become uniformly unbounded as time increases. Instead of working directly with I, however, investigation will be made into conditions under which the time-integrated average of I is 0. This condition is more subtle. A necessary condition for the time-integrated average of I to be 0 is that the time-integrated average of I be 0. What will be shown is that if the uniform charge density has exactly the right size, and the frequency is above a critical value, the time-integrated average of I is exactly 0. A larger value for the charge density would drive the time-integrated average of I negative, leading to collapse and, perhaps, instabilities. This is because the exact value of uniform charge density derived for a null is the same required from classical mechanics to simultaneously satisfy Maxwell's equations and the laws of inertia with finite mass electrons in harmonic motion along field lines. For this reason, the conditions to be derived will be considered sufficient for self-containment. Gurdjieff and Stabler also discuss this point. Substituting the time-dependent R from EQ13 into EQ 11 billions, and taking the time average automatically gives 0 because of the assumption that the charges oscillate with fixed centers implies confinement. It is far more interesting to substitute for the terms in I, assuming harmonic motion for the charges, to calculate conditions for stability. Denote the time-integrated average of a quantity by a bar 5 equal to IR to obtain new information from EQs 11. Note that the terms in the integrand containing F, the acceleration, are related to the volume force on the electrons. The term with 2 can be written porc prom EQs 9, 11, 13, 14, and 15 with a little algebra, hold, in order for the right-hand side of EQ 16 to be 0. The following conditions must K and M, E, LOL equal to 12, 823 to 02, where M, E equal to 5.69 extend to 12 kg, cool is the mass-to-charge ratio for the electra. Equation 17 billions was derived previously, 1. Using a Lagrangian formulatio, from variational considerations introduced in classical mechanics. 2. The result in EQ 17 billions arises from only assuming that the quantities E, H, and J have the force-free form and that the free electrons carrying the current have non-zero mass. Uniform charge density is not an a priori assumption in the Lagrangian calculation. A diversion is needed at this point to discuss the effects of the harmonic electromagnetic field assumed in the present model. The usual analysis involving the virial theorem includes the electromagnetic energy density in the integrand in EQ 10. The assumptions made here are that the electronic velocities are non-relativistic and the harmonic fields E and H are non-zero inside the excitation and 0 outside, which is equivalent to effective electric and magnetic currents respectively equal to Jeff Aksh and 186. Where is the outward-pointing normal to a sharply defined excitation boundary? The first thing to realize is that if such currents existed, they would exactly counteract the electromagnetic stresses at the excitation boundary. The reasoning is that internally the electromagnetic field, terminated by the currents in EQs 18AB, seems to stretch to infinity with a zero-pointing vector, XH 0. No energy is lost to the outside if the currents are maintained. For the lowest, equal to 1 spherical mode at a R1 equal to 4.493. Both E and H are tangential to the boundary, and therefore the stresses due to the internal fields are normal to the surface. The occurrence of the currents in EQs 18AB can be thought of as representing pinches, which barely contain the normal stresses due to the electromagnetic field trapped inside. Viewed in this manner, the surface currents represent a lowering of the energy of the overall system. It is understood that surface currents, while countering the electromagnetic surface stresses, will not null the pressure gradients that arise from variations in the fields, and will tend to produce internal motion. No mechanism can produce ideal surface currents. The present work is primarily aimed at finding the most stable configuration of the charge distribution when electromagnetic stresses and radiation are ignored. Ongoing work appears to indicate that judicious choices of K and A can null the outgoing radiation field and vortical fluid modes can all the electromagnetic stresses. Invoking idealized surface electric and magnetic currents will merely be an A dodge that is temporarily needed to obtain an important result concerning the charge density. These surface currents will not be discussed any further. Returning to the results in EQs 17, It might first appear that if the free charge density were increased beyond the value prescribed in 17b, stability would increase, because I in EQ16 would decrease. If this were to happen, the electromagnetic fields and mechanical trajectories would no longer follow force-free field lines and would no longer be consistent with the model. From the simplest considerations, it was shown that small perturbations, 7, in fluid density did not grow, 2. It will be assumed that if the conditions already discussed are met, with the currents lying in a negative potential well, the excitations under study are stable and only slowly evanescent. It is important now to estimate how close a real physical system can be made to approach the conditions for force-free field approximations on the vector fields E, H, and J. If electrons were massless, the problem would be far simpler, since they would experience no centripetal accelerations and would conform to electric field lines like currents in wires. In reality, the electrons cannot confine their motion to be strictly along the curved field lines of a force-free field. The assumption that the electrons undergo simple harmonic motion along electric field lines becomes more accurate as the frequency increases and the electric field decreases. This can be seen from EQ 13, where the amplitude of the harmonic motion is J, PW. Substitute LG for J in terms of E. A condition for small amplitude oscillations can be written. ELM 493, where LJML is the maximum absolute amplitude of the harmonic electric field within the excitation. Using RLMKS units and a radius, 0 rands equal to 4.493 AEQ 19 becomes LMs equal to 0x0 J2, where C is an appropriately WT-1 factor that satisfies EQ 19, and A is the free pace, wavelength of the harmonic wave. The assumption will be that the smaller the value of C, the longer the lifetime of the excitation, all other things being equal. At this time there are no estimates for lift times, but some reasonable values for the parameters might be ρ equal to 10 centimeters, A equal to 1 millimeter, and C equal to 0.1. Under these conditions, a 10 centimeters radius spherical excitation will have a total energy density on the order of 10 joules. THIM value is larger than average reported energies of ball lightning, and these excitations may represent an electromagnetically excited fluid state that could serve as a model for ball lightning-like phenomena. The total energy in any spherical excitation will be proportional to the factor F equal to 8. This implies that for a fixed ratio of the radius to the wavelength, for the same value of C, the energy content of a spherical excitation is linearly proportional to its radius. Since the volume is linearly proportional to the cube of the radius, the smaller the sphere, the higher the energy density, under the above fixed ratio of radius to wavelength. For the numerical example already given, if the radius were shrunk to 1 millimeter, the total energy content would be about 15,000 joules. The wavelength of the harmonic wave would be 101 ndm, and the energy equivalent to a 50-watt light bulb burning for 5 minutes. Conclusions. A model for electromagnetic ionized fluid excitations predicts the self-containment of high-energy modes in small volumes. The virial analysis yields the same results as self-consistent solution of Maxwell's equations, with current solved with a Lagrangian formulation, allowing the current to be carried by non-zero mass electrons. The important result is that, excluding electromagnetic stress effects, the most stable configuration must have a uniform free charge density that is determined only by the size of the excitation and the frequency of the harmonic electromagnetic field. The artifice of idealized surface currents was used to isolate the internal 6Ls from the outside and prevent radiation. Internal electromagnetic volume stresses were ignored in the analysis. Ongoing work is indicating that if K and A are chosen correctly, then the outgoing radiation field can be nullified. Indications are also that the internal electromagnetic stresses can be cancelled by vortical fluid modes. The excitations will have finite lifetimes, but may persist for a considerable amount of time if losses are not large. Upper limits were set on the maximum electric field strength within an excitation to confine the electronic motion to electric field lines. It is expected that there may be a trade-off between maximum field strength, I, maximum energy density, frequency, and lifetime. Larger field strengths and lower frequencies imply larger excursions of the electrons from electric field lines, leading to volume losses as well as surface losses, with synchrotron radiation probably being very important. Vortical modes may greatly affect lifetimes. Using reasonable input numbers, maximum field strengths and subsequent stored energies are very high, making the production of such excitations look very attractive. It is not clear, however, what a production facility for harmonic force-free excitations might look like, since the internal vortical structure of these excitations is still under investigation. Fireballs reported in the literature, 9, may be candidates for investigating their internal fields to determine whether they fit the harmonic force-free model. Theoretical areas still need to be researched. Radiation rates due to nonlinear fluid effects to be calculated. These rates might set an upper bound to the lifetime of a classical excitation. Although a rough stability analysis was done in a previous paper, 2, a more rigorous analysis involving perturbations of the current remains to be done. This, 9. Woe-iled involve the calculation of restoring forces, if any, that would arise from a physical deflection, as well as other mechanisms that would return the excitation to its original state after a perturbation. Energy losses due to perturbations of the conditions from ideal should be calculated. Much of this depends on the work being done in connection with electromagnetic stresses influencing fluid motion. The idea of applying quantum mechanics to these excitations can be investigated. As the size of the excitations shrinks, quantum effects may become very important, according to Nadi, I.O. If a self-consistent potential is formed by the currents in an excitation, there may be a collective electronic wave function that exactly confines its flux field vectors to the streamlines of a force-free electric field. Quantized in this manner, lifetimes of states may be much larger than would be expected from purely classical considerations. Maximum energy levels may also be much larger. The form of the calculations would probably resemble Hartree-Fock atomic procedures and would ultimately have to include fluid dynamic effects. Further investigations seem to hold great promise. 10. References. 1. Truesdell C. The Kinematics of Vorticity. Indiana University Press, Bloomington, Indiana, 1954. Zaghloul H. and O. Barajas. Force-Free Magnetic Fields. J. Phys. 58783, 1990. 2. Nachamkin J. Non. Radiating Harmonic Fields that Can Confine Plasma Currents and Charges, manuscript, submitted for publication. 3. Harrington, R.F., Time-Harmonic Electromagnetic Fields, New York, M.C. Graw-Hill, 1961. 4. Schmidt G., Virial Theorem for Plasmas. Phys. Fluids, 3. 481, 1960. 5. Rosenbluth, M.N., and G.W. Stewart. Relativistic Virial Theorem, Phys. Fluids, 6. 452, 1963. 6. Gurdjieff E. and R.C. Stabler. Self-Confinement of Plasmas, Phys. Fluids, 7. 920, 1964. 7. Liboff R.L. and T.J. Lai. Plasma Virial and Equations of State for a Plasma, Phys. Fluids, 11. 1943, 1968. 8. Smirnov B.M. Physics of Ball Lightning, SOV. Phys. USP, 33, 4. P261 to 287, 1990. 9. Otsuki, Y.H., and H. Ofuritan. Plasma fireballs formed by microwave interference in air, Nature, Vol. 350. pp. 139 to 141, March 14, 1991. 10. Nadi V. Personal Communication, 1991. 11. Appendix G54, Surface Radiation from Ideal Force-Free Harmonic Electromagnetic Excitations, Jack Nachamkin University of Dayton Research Institute, Phillips Laboratory OLAC, PARKFE Edwards, AFB, CA 93,523 to 6,000. Abstract. Spherically symmetric force-free harmonic solutions to Maxwell's equations may be truncated at a radius where the fields are tangential to a sphere. Equivalent currents, which satisfy the jump boundary conditions between the inner fields and the vacuum, maintain the excitation A, though the inner solution extended to infinity, and prevent radiation flow. Since the Poynting vector is identically so inside the spherical boundary, no energy can escape from the inner volume even if the surface currents were not present. The surface boundary fields can radiate away the energy, however, which is exactly cancelled by the radiation from the surface currents. It will be shown that for any given frequency, an infinite number of chokes for the force-free spherometer are possible such that the far-field radiation from the surface currents is zero. Each of them choices implies a different spherical truncation radius. For large waver numbers, successive possible chokes of truncation radii differ by approximately a half wavelength. For my of those chokes, no surface currents are needed to prevent steady-state radiation. Introduction. It has been shown that Maxwell's equations for harmonic electromagnetic waves with angular frequency W admit solutions having the electric and magnetic fields, E and H, as well as the current, J, in the force-free fermione. A field F has the force-free form if Vxf equal to AF, where A, the force-free constant, is not a function of either space or time. Consider the following solution to EQ. 1. In spherical coordinates, Ra. 1, phi, R9, 4, equal to 1 plus 1, sin minus 1, AR, 1, or A sin R. Gr sin, where I is any integer greater than 0, Giz the familiar spherical Bessel function, and the vectors, and are the familiar right-handed 3D polar coordinate unit vectors. This is not the only solution to EQ. 1, but it has interesting properties. To be specific, let I equal to 1 and A be real. At AR equal to 4.493, R equal to 0, and the field becomes tangential to a spherical surface with radius. R1 equal to 4.493. A, both E and H, can be written as vector fields proportional to F in EQ. 2. By the time factor XP, IIT. This time factor will henceforth be suppressed. If the solution to Maxwell's equations is truncated at R equal to ρ, with 0 fields for R greater than or equal to ρ, the resultant field will continue to be a solution throughout all of space if currents are made to flow on the surface of the sphere at ρ. The equivalent of an electric current, J, and a magnetic current, M, must flow to satisfy the jump conditions in the fields at these currents are defined to be ρ, J equal to AX, and M axi, where E and H are the surface electric and magnetic fields, and A is the outward normal ATR. The physical significance of these currents is discussed elsewhere. 3. From EQs 2 to 5, the surface currents J and M will be proportional to Ju, also known as sin, where Jo, ρ, equal to 0.2172. Under ideal situations, no radiation can escape from the spherical surface if the currents J and M are present. The radiation from these currents exactly cancels the radiation from the surface of the excitation. The reason is that the Poynting vector, S, X, H, is identically equal to 0 everywhere for RR. In the next section, the far-eld radiation from the surface currents will be analysed for the one case. It will be shown that, for appropriate values of RA, the surface currents will not radiate. The suction will be that under certain conditions, surface currents are noted to prevent steady-state radiation from an excitation. Null surface radiation conditions. Defining the wave number W(c), with c being the speed of light, the vector potential in the field for a volume electric current, R, approaches the expression A, R, minus 3, where R is a unit vector in the direction of the point in the far field. R is the distance of the far field point from an arbitrarily chosen centre of the current distribution. R is the vector from the centre of the distribution to the integration point. And when the current distribution collapses to a surface distribution like that in EQ 6, the integral in EQ 8 becomes proportional to the integral, where the distribution is centred at 0 and the integration is over the surface of the sphere R equal to ρ. The integral in EQ8 can be evaluated in closed form by expanding all quantities in the integrand in terms of spherical harmonics, y, in the primed coordinates, and y, in the unprized far-belled coordinates. First, convert the spherical vector into a sum of unit Cartesian vectors and y in the x and y directions. Next, note that sin sine plus sin cos plus the exponential in the integral has the expansion 4r, where the asterisk denotes complex conjugation using the orthogonality property of the spherical harmonics. A little algebra shows that, finally, I minus 4r, where is the unit spherical vector in the far field? If the product k-ri is one of the zeros of g, re, then the vector potential for outgoing waves due to the I, equal to one surface electric current, goes to zero more quickly than the inverse of the distance in the far field. This current will therefore not radiate. An exactly analogous argument shows that the I, one magnetic surface current, will not radiate either if the same conditions are met. In the next section, proof will be given for the general result that the outgoing radiation field from 1 cases can also be nullified. Third, general conditions for null radiation. In the 1 case, the integrations needed to evaluate the far-celled simplified. For any other allowed value of 1, I greater than 1, the integrals involve sums of terms of the type Jz, k, with LOD. Only for I equal to 1 is there a single term in the sum. For higher values of I, then, it is not clear whether the far-field radiation may only be minimized or nulled in any one direction, but cannot rolled out completely in all directions. The anemuthally symmetric I, one mode in EQ, 2, and modes, derived from it by rotations and subsequent linear superposition, are not the only ones for which the surface radiation of a truncated, force-free harmonic excitation can be exactly nullified by a judicious choice of the force-free constant A and the free space wave number without invoking surface currents. This will now be shown by comparing the cells in the above excitations with the internal electromagnetic oscillations of a resonant spherical cavity. 5. The strategy will now be to choose excitations that obey EQ. 1. Choosing Re and K such that Js alpha rho equal to 0 and G k rho equal to 0. Define, now, the complementary vector fields. And n equal to plus 1, consi, 1, k. A solution of Maxwell's equations in a perfectly conducting hollow sphere of radius r equal to ris, em, hi, nv. If EQ, 18, holds, then EQs, 21, represent a resonant excitation of a spherical cavity. The cells represented by EQ, 21, are confined to the region are less than or equal to Re, the electric field, at rise 0. The magnetic field induces a current I, xh, at r rho, where his the outward pointing normal to the spherical surface. This current, considered by itself in unbounded free space, is the only source of the electromagnetic field both inside and outside the spherical cavity. As such, this current cannot radiate into the vacuum region Re, so that the electromagnetic field external to I will remain 0 if it is initially 0. Now note that at rho phi, rho section 4 equal to n1 rho section, consider phi the magnetic field in a force-free excitation where EQs 17 and 18 hold. Radiation from the surface at r, Re, due only to the magnetic field, will entirely depend on the contribution from the term equal to x Re, where A is the outward normal to the sphere at r. Since h, rho, equal to 0, it does not contribute, s, from the above argument involving I. If the external radiation field, due to the surface contribution from the magnetic component of a force-free excitation, is initially 0, it will remain 0. Exactly analogous arguments apply to the electric field contributions to the external radiation. Fourth discussion. The conclusion to be drawn is that ideal spherical electromagnetic force-free excitations can exist with no E-mal radiation field for all values of I in EQ. 2. Equation 2 has no azimuthal variation. It is not difficult to generalize M and N in EQS, 19, and 20, and thereby F, using the formulas on page 416 of Stratton's book. None of the arguments change when azimuthal variation is introduced, so that all the results derived for modes with no azimuthal dependence carry over to the modes having any consistent dependence on the angle 4. For reasons of simplicity, all comments will henceforth be directed toward the I, one case having no azimuthal dependence. This is the mode with the lowest symmetry and least complicated geometry. The surface fields topologically are equivalent to inviscid fluid blow lines over a rigid sphere. Since the mode was truncated at the first zero of the JI-AR function, it is easy to see that a necessary condition for nullifying surface radiation is K2, 21. Below a certain frequency, for a given A, the surface radiative losses cannot be nulled unless the K equal to 0 or zero frequency case is allowed. It has already been shown that for Ka the interaction energy of the volume harmonic current and the oscillating magnetic field has a negative value everywhere within the excitation. 3. In other words, the current lies in a negative potential well, whose relative depth increases with frequency for Ka. This potential is positive for Ka. Although it has not yet been tested, this presumably means that K a case is more stable than the K a case. It is interesting that surface radiation can only be nulled in what is presumably the stable region. Outside the excitation, there are null fields. When non-zero mass electrons are introduced as harmonic current carriers, as the actual physical situation demands, certain energy loss mechanisms can be identified. 3. It is evident that if force-free harmonic excitations can be manufactured in a form that resembles spherical plasmoids, it is most likely that A and K will have to be tailored in the manner described in this note to prevent radiation losses. 7. References. 1. Nachamkin J. Non-radiating harmonic fields that can confine plasma currents and charges. Manuscript submitted for publication. 2. Harrington R.F. Time-Harmonic Electromagnetic Fields, New York. M.C. Graw-Hill, 1961. 3. Nachamkin J. Virial Analysis of Harmonic Force-Free Excitations. Manuscript submitted for publication. 4. Rose-Me, Elementary Theory of Angular Momentum, New York. J. Wiley. Sons, 1957. Stratton Essay, Electromagnetic Theory, New York. M.C. Graw-Hill, 1941. References. 1. Bostic 1. The Experimental Study of Plasmoids, Phys. Reverend 106, 404, 1957. 2. Bostic Whopper, Plasmoids, Scientific American, October. 1957, p. 87. 3. Bostic What, and Others, Second International Conference on Energy Storage Compression and Switching, Venice, Italy. New York, Plenum Press, 1983, Puthoff, He, Condensed Charge Technology and Its Potential Impact on the Electronics Industry. Meeting of the Society for Scientific Exploration, Palo Alto, June, 1990. 4. Kapitsa, P.L., The Nature of Ball Lightning, Dokel. Akkad, Nox SSR 101, 245, 1955. 5. Actually Symmetric Force-Free Plasmoids, Phys. Fluid 7, 826, 1964. Stratton, Essay, Electromagnetic Theory, New York, M.C. Graw-Hill, 1941, 7. Bachelor G.K., An Introduction to Fluid Dynamics, Cambridge University Press, 1967. 8. Tsuji Y. Force-Prey Magnetic Field in the Axisymmetric Torus of Arbitrary Aspect Ratio, Phys. Fluids 12, 3379, 1991. 9. Rosenbluth M.N. and M&M Busak, MHD Stability of Spheromac, Nuclear Fusion, 19, 489, 1979. 10. Truesdell C. The Kinematics of Vorticity, Indiana University Press, Bloomington, Indiana, 1954, 11. Zaghloul, H. and O. Baraja, Force-Free Magnetic Fields, AM, J. Phys. 58, 783-788, 1990, and references therein. In a similar vein, the paper by Shimoda K., Kawai T., and Uehara K., Electromagnetic Plane Waves with Parallel Electric and Magnetic Fields EH in Free Space. AM, J. Phys. 58, 394-396, 1990, deals with vacuum plane wave fields with no currents and infinite extent. Their solutions do not have the force-free form, however, and it is not clear that such solutions could be the basis of a theory of plasmoida. 12. Nachamkin J. Non-radiating harmonic fields that can confine plasma currents and charges. Manuscript, Su. Mitted for publication. 13. Nachamkin J. Surface radiation from ideal force. Free harmonic electromagnetic excitations. Manuscript, submitted for publication. 14. Schmidt G. Virial theorem for plasmas, Phys. Fluids, 3, 481 1960 55, 15. Rosenbluth M.N. and G.W. Stewart, relativistic virial theorem, Phys. Fluids, 6, 452 1963, 16. Gurdjieff, E. and R.C. Stabler, self-confinement of plasmas, Phys. Fluids, 7, 920, 1964, 17. Liboff, R.L. and T.J. Lai. Plasma virial and equations of state for a plasma, Phys. Fluids, 11, 1943, 1968, 18. Nachamkin J. Virial analysis of harmonic force-free excitations, manuscript, submitted for publication. 19. Javid M. and P. M. Brown, Field Analysis and Electromagnetics, M.C. Graw-Hill Book Company, 1963. 20. Stacy, W. M. Fusion Plasma Analysis, New York, Wiley into Science, 1981. 21. Gecker L. R. Interaction of Strong Electromagnetic Fields with Plasmas, Oxford, Clarendon Press, 1982. 22. Second Annual Workshop on Advanced Propulsion Concepts, National Aeronautics and SPA, Administration, Jet Propulsion Laboratory Publication, JPLD to 8052, November 29, 1990. 23. Harrington, R.P., Time-Harmonic Electromagnetic Fields, New York, M.C. Graw-Hill, 1961, 24. Smirnov, B.M., Physics of Ball Lightning, SOV. Phys. USP. 33, 4. P. 261 to 287, 1990. 25. Rose, Me, Elementary Theory of Angular Momentum, New York, J. Wiley and Sons, 1957. 25. Van Bladel J. Electromagnetic Fields, New York, Hemisphere Publishing Corporation, 1985.